The reef begins long before the eye notices its edges. It is felt first as a thinning of the water, a subtle shift in temperature and clarity, a tightening of the currents that thread between coral towers and swaying gardens of seagrass. Light fractures into wavering ribbons that tremble over the sand, and shadows bloom in impossible shapes. The camera drifts forward, settling into a shallow cove where a boulder sits half buried in the sediment, draped in algae and crusted with barnacle scars. It looks still, inert, unimportant. But stillness in the ocean is often camouflage, and in this case the apparent rock is a lie waiting to unfold. A faint ripple along its edge betrays movement. A texture changes, a pattern shifts, and the object that was stone a moment ago exhales a slow, calculated pulse of water. The octopus reveals itself only when it chooses to, peeling away a disguise that would fool almost any creature that approaches. What makes this animal so effective at vanishing is not just mastery of color, but the distributed intelligence woven through its body. An octopus is not a creature ruled by a single central brain dictating every movement. Instead, its nervous system spreads through each arm, with clusters of neurons that process information locally. This means a single arm can taste, touch, respond, and execute complex movements without waiting for permission from the central brain. In practice, this creates a creature that thinks in parallel, analyzing its environment from 8 different vantage points simultaneously. It is as if the octopus carries a team of independent problem solvers beneath its skin, each one capable of acting on its own but coordinated enough to appear seamless. This decentralized design evolved in predators that must adapt instantly to a world of shifting terrain and unpredictable threats, where the difference between life and death can be the ability to squeeze through a crevice barely wider than an eye. The body itself seems engineered for improvisation. Without a rigid skeleton, the octopus bends, flattens, elongates, and compresses into shapes that defy ordinary classification. Muscles run in layers, oriented in directions that allow twisting, pulling, and coiling far beyond what vertebrates can achieve. When an octopus approaches a narrow crack in the reef, the decision to enter is not a hesitation, but an evaluation. The arms probe first, tasting chemical signals, measuring the interior dimensions, mapping surfaces with suckers that function as tactile sensors and chemical detectors simultaneously. If the space offers possibility, the entire animal dissolves into a flowing ribbon of flesh, pouring itself into the crevice as though liquid rather than living tissue. What emerges on the other side is not a creature that squeezed through, but one that simply reshaped its existence to fit the available world. This malleability becomes most striking during hunting. The cove brightens as the sun shifts overhead, sending beams deep into coral canyons where small fish gather in schools that swirl like drifting clouds. The octopus remains still, skin flickering between colors that match the mottled reef. Patches of beige, streaks of russet, scattered speckles of white. Then the transformation deepens. Muscles contract to create raised bumps, mimicking coral polyps. Light-reflecting cells shift the surface sheen to mirror the substrate. In seconds, the octopus becomes a section of reef so convincingly sculpted that passing damselfish ignore it completely. When the moment is right, an arm extends with the slow certainty of a shadow growing at dusk. The suckers grip the rock to anchor its body, while another arm drifts outward like a vine in slow motion. The octopus studies the fish, predicting their movements. It is a hunter that relies not on speed alone, but on strategy. An animal that learns from experience, remembers locations, and recognizes patterns in prey behavior. The central brain integrates signals from the arms, deciding when to strike. Once the decision forms, the body reacts as a unified force. The octopus launches forward, enveloping the fish in a hood of muscle and membrane. A cloud of silt erupts, then clears to reveal the empty coral where the prey once hovered. The capture is swift, clean, and entirely dependent on the octopus's ability to become invisible until the final heartbeat. The same intelligence that makes the octopus a formidable hunter also makes it a notorious escape artist. In aquariums, keepers tell stories not because they are rumors, but because they are common enough to be unsurprising. An octopus notices a tiny gap in a tank lid. Its arms explore the edges, calculating the necessary compression. It slides upward, suckers adhering to glass, each movement deliberate. Once outside, it navigates by memory and tactile cues, using the moisture on its skin to move across the floor in search of a drainage pipe or another tank filled with fish. The octopus's exploration is not random. It is guided by problem solving that rivals some vertebrates traditionally recognized as highly intelligent. It understands cause and effect. It tests variables. It repeats behaviors that lead to reward. In controlled studies, octopuses learn to open jars, manipulate latches, solve mazes, and distinguish between shapes. These are not party tricks, but reflections of evolutionary pressure. The ocean rewards adaptable thinkers, especially those vulnerable to larger predators. Camouflage remains the octopus's first line of defense, and its skin is a marvel of rapid communication between the brain and specialized pigment cells. Chromatophores expand or contract to display reds, browns, or yellows. Beneath them, iridophores reflect shimmering blues and greens, while leucophores scatter ambient light to mimic surrounding brightness. This multi-layer system allows the octopus to match not just color, but also reflectivity and pattern complexity. A predator approaching from above sees what appears to be a patch of sand or coral. A predator looking sideways encounters the outline of a rock. In environments with shifting light, such as shallow reefs where surface ripples distort the sun, the octopus adjusts in real time, updating its disguise with each passing second. Certain species push this ability even further through mimicry. A lone octopus glides over a sandy clearing, its body narrowing, arms trailing behind in a tapered formation. The transformation is uncanny. The animal now resembles a venomous flatfish. When threatened, it may imitate the posture of a lionfish, spreading its arms to mimic spines. In another moment, it shapes itself into the form of a sea snake, displaying contrasting band patterns. These imitations are not perfect replicas, but they are close enough to activate the instinctive avoidance behaviors of potential predators. The octopus does not need to convince an observer of exact identity. It only needs to trigger the correct fear response. This is evolutionary bluffing at its finest. Beneath the mimicry lies an understanding of space that goes beyond reflexive responses. The octopus can plan a route through unfamiliar terrain, identify hiding places, and return to den sites after long excursions. It arranges shells and rocks outside its lair, creating a barricade that functions as both camouflage and protection. When disturbed, it may deploy ink that serves multiple purposes: visual obstruction, chemical deterrent, and even a decoy shaped roughly like its own body. The ink contains compounds that dull the sensory systems of predators, especially those that rely on smell, buying the octopus the seconds it needs to vanish. As the tide turns and currents strengthen, the reef fills with new activity. Schools of fish shift their orientation, predators begin their patrols, and the octopus prepares for another hunt. The camera follows as it squeezes into a crevice no wider than a small coin, disappearing from sight. Inside, the octopus navigates a world of narrow passages and hidden chambers. It encounters a crab grazing on algae. In an instant, an arm darts forward, suckers wrapping around the shell. The animal delivers a bite infused with venom, designed not to kill outright, but to paralyze, allowing it to pry open the shell with methodical precision. The venom contains enzymes that break down muscle tissue, simplifying the meal into a digestible slurry. Many viewers imagine venom as a weapon of aggression, but in this case it is a tool of efficiency, an adaptation that allows the octopus to access food sources protected by tough exoskeletons. Throughout this environment, the octopus's awareness remains distributed. Even as one arm manipulates food and another secures the den entrance, the rest explore, taste, and evaluate the surroundings. If a predator casts a shadow across the opening, the animal does not panic. Instead, it withdraws into darkness, blending with the rock face. The octopus becomes an absence, a negative space shaped like a crevice. And when danger passes, it resumes its work as though nothing interrupted it. What emerges from this world is an understanding of intelligence shaped not by social structure, as in primates or dolphins, but by solitude and vulnerability. The octopus does not rely on a group for safety or shared learning. It must interpret its environment without guidance, solve problems independently, and navigate landscapes that change daily. This creates a mind tuned for creativity, improvisation, and risk assessment. Every decision carries weight, every movement reflects calculation. In the final minutes of the scene, the camera returns to the initial cove where the octopus first revealed itself. The tide has shifted, carrying new sediments that settle over the coral. The octopus slides along the sand, its body shifting between patterns like a painter testing palettes. A moment later, it becomes stone once again, indistinguishable from the environment that created it. This is the essence of the octopus, an animal that thrives by refusing to commit to a single shape, a single strategy, or a single way of thinking. Its power lies in fluidity, and fluidity is a kind of genius all its own. The first hint of the cuttlefish is not a shape, but a flicker, a ripple of light that skims along a patch of seagrass and vanishes before the eye fully registers it. The camera drifts deeper, letting the ambient blue fade into the green glow of a sheltered coastal bed where sand and algae weave a shifting mosaic. Tiny particles suspended in the water catch the sunlight and tumble like dust motes in a hidden cathedral. From this haze, a creature materializes not through movement, but through the sudden interruption of stillness. A slab of shimmering texture brightens, darkens, then collapses into the exact pattern of the sand beneath it. The cuttlefish appears, as though the environment exhaled it into existence. Cuttlefish camouflage is an entirely different phenomenon from that of the octopus. Where octopuses rely on deceptive stillness and sculpted texture, cuttlefish lean into motion, the deliberate, orchestrated motion of light across their bodies. Their skin is not a passive canvas, but a living screen, capable of producing waves of brightness that roll from head to tail with astonishing speed. Chromatophores, iridophores, and leucophores form a multi-layered display system that operates like a biological LED panel. Each pigment cell responds to neural commands that travel faster than most creatures can blink. What results is a flickering language of bands, flashes, and oscillating bars that sweep over the animal with such precision that prey often freeze in confusion, unable to process what they are seeing. This hypnotic display is not accidental. It is a carefully tuned hunting strategy that exploits how small fish and crustaceans interpret visual cues. Many prey species rely on consistent contrast and motion direction to detect threats. The cuttlefish disrupts that ability by sending contradictory signals in rapid succession. A band of dark pigment pulses forward, a wave of bright white follows, then the entire pattern reverses direction. The prey's brain attempts to track the movement but fails, as the patterns exceed the neural processing limits of most animals. This moment of confusion opens a narrow window of opportunity. In that suspended instant, the cuttlefish glides forward with arms splayed, tentacles coiled like springs. When the strike occurs, it is not seen until it is already over. The environment around the cuttlefish reveals why such precision is necessary. Shallow coastal beds are noisy places in ecological terms. Light refracts unpredictably through surface ripples. Shadows of drifting seaweed confuse depth perception. Countless small animals dart, flick, and hover. In this kaleidoscope of competing visual signals, a predator must manipulate perception rather than overpower it. The cuttlefish dominates this arena not through brute force, but through sensory mastery. Its eyes, shaped into distinctive W-shaped pupils, adjust to everything the ocean throws at them. This strange geometry maximizes contrast in murky water, reducing glare and splitting light into usable segments even when the water column is thick with particles. The shape also expands depth of field, giving these animals an unusually stable image even when the body sways gently with the current. The visual world of a cuttlefish differs from ours in another profound way. While humans perceive primarily color and brightness, cuttlefish detect polarization, the orientation of light waves as they pass through the water. Many fish scales reflect polarized light strongly, creating signatures invisible to most predators but glaringly obvious to cuttlefish. In effect, a cuttlefish sees glowing outlines where we would see muted shapes. This heightened ability allows them to detect prey buried in sand, to read social signals from rivals, and to communicate covertly through polarized flashes that other species cannot interpret. It is a hidden channel of vision layered atop the already complex patterns flowing across their skin. The camera follows a lone cuttlefish moving through a corridor of gently waving seagrass. As it glides, the light pulses along its mantle with rhythmic regularity. The arms at the front remain poised, forming a tent of sensory exploration. Beneath them lies the beak, a compact and efficient tool capable of cracking crustacean shells or slicing fish with surgical precision. But the cuttlefish rarely relies on direct confrontation. Instead, it manipulates its surroundings so thoroughly that the prey exposes itself voluntarily. A small shrimp, alerted by the flickering display, backs away instinctively, only to stumble directly into the reach of the waiting arms. In the blink of an eye, the tentacles snap forward, extend, grip, and pull the prey inward with astonishing speed. For all their hunting prowess, cuttlefish exist in a world where every strategy must serve multiple purposes. Their changing displays are not just weapons, but communication systems. When two males encounter each other during the breeding season, the visual exchange becomes a duel of shifting patterns. The bands intensify, the contrast sharpens, entire sections of the skin flash like warning beacons. These displays are not arbitrary aggression, but a calculated attempt to establish dominance without escalating to costly combat. Each pulse conveys information about size, strength, and willingness to engage. Because cuttlefish grow quickly and have short lifespans, conserving energy and avoiding injury are crucial for survival. A fight avoided is a season extended. Yet the cuttlefish possesses one social tool more bizarre than almost anything else in the animal kingdom: the split body display. The scene shifts to a clearing where a female hovers near a cluster of algae-covered rocks. Two males circle her, patterns flashing, each attempting to outshine the other. A third male lingers at the edge of the frame, smaller and less imposing. If he were a more straightforward creature, he might retreat. Instead, he performs a deception so sophisticated that it appears almost theatrical. The side of his body facing the female shimmers with soft courting pulses, subtle and inviting. The side facing the rival male turns dark and aggressive, mimicking threat patterns to deter interference. The result is a creature that broadcasts two completely different messages simultaneously. This dual-channel broadcast allows the smaller male to slip past larger competitors and mate successfully, an evolutionary workaround driven by the relentless pressure of competition. This trick works because each side of the cuttlefish's body is controlled semi-independently. Neural pathways allow the animal to isolate pattern commands so completely that one half of the skin behaves as though it belongs to a different individual. No vertebrate can achieve this level of split display. It is a distinctly cephalopod innovation, rooted in the fine control cuttlefish maintain over thousands of pigment cells across their mantle. The environment responds to these shifts. When the smaller male slips toward the female, the larger rivals intensify their own patterns in frustration, sending bold bands rolling down their mantles. The female watches with an unblinking calm that conceals layers of evaluation. Her survival depends on selecting a mate capable not only of producing viable offspring, but also of navigating the treacherous social landscape without drawing unnecessary predators. A male who courts cleverly without attracting too much attention may offer better prospects than a brightly flashing rival who risks everything on speed and aggression. Far from these social dramas, another cuttlefish drifts slowly along the sandy bottom. This one is hunting through stillness rather than through motion. Its body is mottled to match the grain and shadow of the substrate, its arms slightly spread to mimic the uneven edges of a buried rock. It does not pulse or flicker. Instead, it waits for a crab to wander within reach. When the moment arrives, the cuttlefish unleashes a burst of rapid patterning, designed not to confuse prey, but to disorient it through shock. The crab freezes. A split second later, the strike lands, tentacles flaring out in a coordinated burst of precision. This duality, the ability to weaponize both motion and stillness, gives the cuttlefish extraordinary flexibility in survival. They are neither ambush predators nor pursuit hunters exclusively. They adapt to the landscape, the light conditions, the abundance of prey, and the presence of rivals. Their behaviors shift with such fluidity that studying them requires constant attention. No two displays are exactly the same, because each one arises from the immediate sensory context, processed through a nervous system designed for instantaneous response. The cuttlefish's internal structure supports these feats. Unlike the octopus, the cuttlefish possesses an internal cuttlebone, a porous structure that regulates buoyancy through controlled gas exchange. This adaptation allows for near-neutral buoyancy, letting the animal hover effortlessly in mid-water without expending much energy. The ability to remain perfectly still, suspended between the seafloor and the surface, enhances its camouflage and stabilizes its hypnotic displays. When the cuttlefish pulses patterns, the movements travel across a body that remains eerily motionless, amplifying the illusion that the waves of light come from the water rather than the animal. As the camera pulls back, the scene expands to reveal a meadow of seagrass, punctuated by scattered coral fragments. The shifting tapestry of patterns plays across multiple cuttlefish now, each one interacting with the changing light. Juveniles adopt softer patterns, learning through trial and error how to imitate the adults. A predator, perhaps a larger fish, approaches. Instantly, the cuttlefish nearest to it flares into a startling display, a high-contrast flash meant to startle and disorient. The predator hesitates just long enough for the cuttlefish to vanish into the background. The reef breathes around them, currents shift, light dims as the sun tilts lower. As evening begins to settle across the shallow beds, the cuttlefish tone down their displays, adopting muted patterns that blend seamlessly with the fading light. The hypnotist screens fade into shadow, becoming indistinguishable from the rippling seagrass and the undulating sand. For a moment, the entire world seems to settle into a quiet equilibrium, until another flicker of light ripples across a mantle, reminding the viewer that beneath every calm surface lies a mind built for manipulation, perception, and deception. The cuttlefish is not merely an imitator or a flash of color. It is a creature defined by the intersection of biology and illusion, a master of perception shaped by the evolutionary arms race of predators and prey. Its patterns are not decorative, but strategic. Its eyes do not simply see, but interpret layers of hidden information. Its behavior does not follow a single script, but adapts to every challenge the ocean presents. In a world defined by uncertainty, the cuttlefish survives by rewriting the rules of visibility itself. The shallow reef looks peaceful beneath the midday sun. Waves roll overhead in slow, rhythmic arcs that scatter bright light into trembling patterns across the sand. Small fish drift cautiously among the coral heads, weaving in and out of cracks that promise both safety and ambush. It is a calm scene, deceptively soft, until the camera lowers toward a patch of seabed where grains of sand jump upward in tiny bursts. Something beneath the surface is digging. A plume of sediment swirls outward. Then, from the darkness of a narrow burrow, two iridescent eyes rise like twin satellites scanning a foreign horizon. This is a mantis shrimp, though the name does little justice to the creature staring back. Every part of its anatomy feels engineered rather than grown, from the armored carapace to the specialized forelimbs folded tightly against its body, hidden weapons capable of releasing enough force to shatter shells, limbs, and even aquarium glass. To understand the mantis shrimp is to understand the physics of violence in an aquatic world. These animals are divided into two principal categories: smashers and spearers. Smashers wield club-like appendages hardened through layers of mineralized material arranged in a helicoidal pattern, a biological architecture that distributes impact stress with extraordinary efficiency. Spearers, in contrast, carry barbed, blade-like arms built for impaling soft-bodied prey. This chapter focuses on the smashers, whose punches accelerate with such speed that they cross the water in a fraction of the time it takes a human eye to blink. As the limb extends, it reaches velocities comparable to a bullet fired from a handgun, generating immense pressure at the moment of contact. But the punch is only the first half of the weapon. The true devastation comes from the cavitation bubble that forms when the strike moves faster than the water can fill the void behind it. This bubble collapses instantly, releasing a shockwave strong enough to stun or kill prey, even if the initial swing misses. In that collapse, temperatures spike briefly to levels comparable to the surface of the sun, and tiny flashes of light, a phenomenon known as sonoluminescence, shimmer for a microsecond. The mantis shrimp does not produce this light intentionally, but its presence reinforces how alien this predator seems. It turns the water into a battlefield where physics itself becomes a weapon, creating lethality in both direct and indirect ways. For creatures that rely on rigid exoskeletons for defense, such as crabs and snails, encountering a smasher mantis shrimp is like facing a living jackhammer designed to exploit structural weaknesses. The camera sinks lower, offering a clearer view of the burrow that houses this underwater warrior. Unlike the drifting lifestyle of many reef fish, mantis shrimp are engineers. They excavate tunnels beneath rocks and coral slabs, using scooping motions of their maxillipeds to move sand grain by grain. The length and shape of the burrow depend on species and habitat, but most share common features: a central chamber where the shrimp rests or guards eggs, a narrow entrance for defense, and extended lateral chambers used for ambush or escape. The walls of these tunnels are often reinforced with compacted sediment, algae, or fragments of broken shells, a natural armor shaped through persistence rather than chance. From this vantage point, the mantis shrimp becomes more than a hunter. It becomes an architect building a permanent fortress in a world shaped by constant threat. When a potential predator approaches, perhaps a larger fish shadowing the entrance, the mantis shrimp withdraws, positioning itself just behind the threshold. The clubs fold tightly against its chest, ready to fire outward in an instant. Should the threat grow too bold, the shrimp strikes the intruder with a blast of kinetic force that sends vibrations spreading through the sediment. Most predators avoid repeating the mistake. The burrow becomes a territory, defended with precision and confidence, and the surrounding sand bears the subtle marks of the shrimp's maintenance work. Mantis shrimp remain alert to every shift in water movement, sensing approach through vibrations transmitted along the sediment. The burrow funnels these vibrations toward the entrance, turning the tunnel itself into a sensory device, amplifying clues about what moves outside. But the mantis shrimp's true evolutionary masterpiece is not its punch. It is its eyes. Perched atop flexible stalks, the eyes rotate independently, scanning the world with near continuous motion. Each eye is divided into multiple sections, including a specialized midband region that detects wavelengths far beyond human perception. Where humans see only combinations of red, green, and blue, mantis shrimp perceive a spectrum that includes ultraviolet and various intermediate hues we cannot imagine. Their visual world is not simply more colorful, it is structurally different. They can detect polarized light in multiple orientations, reading patterns invisible to other predators and prey. This ability allows them to interpret subtle reflections off fish scales, to recognize circularly polarized markings used for intraspecies communication, and to detect transparent or camouflaged organisms that would otherwise escape attention. Polarization vision also aids in hunting. Some prey, such as shrimp or transparent fish larvae, distort polarized light when they move. The mantis shrimp sees these distortions as bright outlines in an otherwise cluttered environment. A predator that perceives the world through polarization gains a map of hidden motion, a crucial advantage in shallow waters where sunlight scatters unpredictably. Researchers studying mantis shrimp eyes often describe them as one of nature's most complex optical systems, and the claim is not exaggerated. Each eye contains numerous photoreceptor types, arranged in layers that refine information far more efficiently than typical vertebrate systems. The camera follows the mantis shrimp as it emerges slowly from its burrow. Its posture blends caution and confidence, each movement measured precisely. It approaches a shell half buried in the sand. With a quick sweep, it pushes aside the sediment, revealing a small snail tucked safely inside. The shrimp assesses the shell's thickness, rotating it with delicate gestures before raising one club. The strike lands with explosive force. The shell fractures instantly, shards spinning outward like splinters from a shattered stone. Before the snail can react, the shrimp delivers a second blow, breaking the structure into manageable pieces. The meal is secured through a combination of accuracy, strength, and anatomical engineering that makes even hard-shelled defenses seem flimsy. Elsewhere in the reef, rival mantis shrimp engage in territorial disputes. When two individuals encounter each other, they rarely escalate immediately to lethal combat. Instead, they perform a ritualized display where they raise their bodies and extend their clubs forward, presenting their size and weaponry. These displays serve to assess the opponent's strength. Because their punches are so destructive, actual fights would risk severe injury to both participants. Nature often favors ritual over reckless escalation when weapons become too dangerous. If neither individual retreats, they may engage in controlled striking against each other's armored exoskeletons, testing durability. The loud cracks resonate through the water. Eventually, one shrimp withdraws, ceding the territory and avoiding unnecessary destruction. The ecological role of mantis shrimp extends beyond predation and territorial defense. Their burrowing reshapes sediment composition, aerates the substrate, and creates microhabitats for small organisms. Worms, amphipods, and juvenile fish often shelter in abandoned or partially excavated tunnels. Over time, the reef floor becomes a mosaic of chambers and passageways, created by countless generations of digging crustaceans. This engineering contributes to nutrient mixing and influences local biodiversity. In ecosystems rich with coral rubble and shifting sands, mantis shrimp serve as ecosystem architects as much as predators, altering the landscape in subtle but meaningful ways. As the camera sweeps across the reef, another mantis shrimp appears in view, this one more brightly colored. Its carapace glows with iridescent greens, blues, and reds that shimmer in the fractured sunlight. These colors do not exist solely for display. They interact with polarized light in ways that communicate identity, reproductive status, and even emotional state. To humans, the colors appear merely vivid, but to other mantis shrimp, they form a sophisticated language embedded in the spectrum itself. When two individuals face each other, their coloration and polarized markings transmit silent information long before any physical encounter occurs. The scene shifts to twilight, where the mantle of filtered blue deepens into an otherworldly gradient. Many reef creatures slow down as light fades, but the mantis shrimp remains active. Its eyes adjust to dim conditions with rapid shifts in sensitivity, allowing it to hunt even when visibility declines. A small fish drifts too close to the burrow. The mantis shrimp lunges forward in a blur of motion. The punch comes so quickly that the fish is struck before its fins react. Shockwaves ripple through the water, tiny cavitation bubbles flaring briefly before collapsing into nothingness. The night brings new interactions. Some species of mantis shrimp leave their burrows to forage under cover of darkness. Their stalked eyes sweep across the quiet seabed, interpreting faint, polarized reflections that betray the presence of prey. In this low-light environment, their visual system becomes an even greater asset. Where most animals rely on silhouettes or chemical cues, mantis shrimp perceive the world in layers of hidden contrast. Sand particles flicker with the interference patterns of polarized moonlight. Crustaceans glow faintly in the shrimp's specialized vision. The entire reef becomes a radiant grid of signals invisible to ordinary perception. The chapter closes with a return to the burrow. The mantis shrimp settles into its chamber, arranging bits of shell around the entrance. These fragments serve as both barricade and building material. The shrimp's clubs tuck beneath its body, ready to unfurl at the slightest disturbance. The ocean around it continues its restless motions, but inside the burrow lies a world defined by vigilance, precision, and the relentless physics of impact. The mantis shrimp survives not through size or stealth alone, but through a combination of engineering, sensory mastery, and raw mechanical force unlike anything else in the marine realm. This creature, often overlooked due to its size, embodies an evolutionary experiment in weaponry and perception. It is an animal that wields physics as a tool, that sees light in patterns few organisms can comprehend, and that shapes the seafloor with the same intensity it brings to its hunts. In the quiet of the reef, where sand settles gently and currents whisper past coral heads, the mantis shrimp remains alert, carrying within its compact frame the power to reshape its world with a single, devastating strike. The lagoon looks harmless in the morning light. Soft turquoise water rolls over patches of seagrass, each blade moving with the steady rhythm of an underwater breeze. Small invertebrates drift in lazy spirals, and the shadows of passing fish wobble on the sandy floor beneath them. Nothing hints at danger. Nothing suggests that beneath this postcard, tranquility lives a creature whose defense mechanism is so extreme, so biologically peculiar, that it borders on absurdity. The pufferfish appears suddenly from behind a rock, a small, round-headed animal with gentle eyes and a faint, hesitant wiggle in its swim. It does not move with the confident speed of a predator. Instead, it looks almost embarrassed by its own shape. A slow, hovering balloon that seems one misplaced fin beat away from floating helplessly upward. The pufferfish's unassuming appearance is the beginning of its evolutionary deception. Many marine animals carry warning colors, sharp spines, or intimidating silhouettes to broadcast the danger they represent. The puffer does none of this. It drifts quietly, relying on subtle camouflage and a reputation that predators learn only once, if they survive the encounter. Its body is tightly packed with tetrodotoxin, one of the deadliest substances produced in any organism. This neurotoxin is not made by the fish itself, but by symbiotic bacteria living within its tissues, particularly in the liver, skin, and gonads. Through generations of coevolution, the fish has become a biological reservoir of poison, powerful enough to shut down nerve signaling across the body of any creature that consumes it. A small amount can stop a human heart. A little more can paralyze the respiratory muscles entirely. Yet the puffer carries this chemical storm with no ill effect. Its physiology adapted to resist the very toxin that protects it. The camera follows a young puffer weaving through the seagrass. Its movements are slow but deliberate, relying on a combination of pectoral fins, dorsal fin, and anal fin to control direction. Unlike streamlined fish designed for speed, puffers have no need for burst swimming. Their defense is not escape, but escalation. When threatened, the pufferfish activates a response that appears comical at first glance, but is the product of intricate anatomical engineering. Beneath its skin lies an expandable stomach, capable of increasing to several times its normal volume. The walls of this organ are reinforced with collagen fibers that prevent tearing during inflation. When danger appears, perhaps a predatory snapper or a curious shark, the puffer reacts instantly. The transformation begins with rapid gulps of water. Muscles around the esophagus clamp shut to prevent the incoming water from passing further into the digestive tract. Instead, the water fills the stomach, causing the body to expand dramatically. The fish swells upward and outward, shifting from a compact form into a nearly perfect sphere. Flattened skin stretches, tiny spines stiffen, and the fish becomes a floating, ungraspable orb. A predator attempting to swallow a puffer in this state finds its mouth filled with stiff spikes and an object several times larger than anticipated. For many predators, the surprise alone is enough to abort the attack. For others, the physical impossibility of swallowing the suddenly enormous prey forces retreat. This inflation is not without consequence. A puffer cannot maneuver effectively while expanded. It cannot escape, hunt, or even maintain proper buoyancy. Inflation is a final barrier, a desperate move akin to barricading a door during the last minutes of a siege. The fact that the strategy works so consistently speaks to the power of deterrence in marine ecosystems. Predators learn quickly. A puffer's lineage benefits from every failed attempt by a predator to consume it. Knowledge spreads through a population, not through instruction, but through pain and trial, and predators soon recognize the distinctive shape of a puffer before it expands. Some carnivorous fish will even abandon pursuit at the first glimpse of its silhouette, knowing the inflated sphere cannot be handled, and the uninflated version is too dangerous to attempt. Yet the inflation is only a physical strategy. The real defense lies deeper, embedded in the molecular structure of tetrodotoxin. This compound blocks sodium channels in muscle and nerve cells, preventing the propagation of electrical signals required for contraction. Once ingested, paralysis spreads from peripheral nerves to respiratory centers. In many animals, death follows swiftly. There is no evolutionary antidote for most predators. Only a handful of species, including certain snakes and leopard sharks, exhibit partial resistance. Everything else relies on avoidance. The puffer's body, tiny as it may seem, holds enough toxin to kill many humans. And still, despite this danger, certain people deliberately seek it out as a delicacy. The cultural phenomenon of consuming pufferfish, known as fugu in parts of Asia, is a contradiction that underscores humanity's willingness to gamble with biology. Skilled chefs undergo years of specialized training to remove the toxic organs with precision, leaving behind flesh that is considered a culinary prize for its texture and subtle flavor. The margin for error is razor thin. A single trace of tetrodotoxin left behind can cause tingling sensations, numbness, or far worse. Even today, after countless warnings, accidents occur. It is a strange irony that a fish whose entire evolutionary strategy revolves around preventing predation becomes an object of intentional risk for humans seeking thrill and prestige. The puffer's role in the ecosystem, however, extends far beyond its notoriety as toxic prey. Many puffers graze on algae and small invertebrates, shaping the microhabitats they inhabit. Some species possess beak-like dental plates that allow them to crush coral fragments and shelled organisms, influencing the distribution of algae by cropping grazing surfaces. Their feeding behavior contributes to sediment production in reef environments, subtly sculpting the seafloor. While they may appear clumsy, their ecological impact is delicate and continuous, woven into the daily rhythms of the reef. The camera shifts to a deeper section of the lagoon, where the water grows dimmer and the sand transitions into coral rubble. A larger puffer swims cautiously along the bottom. Its eyes, large and expressive, rotate independently, scanning the environment with remarkable clarity. Puffer fish vision is adapted for precise depth perception, crucial for navigating tight spaces and accessing small invertebrates. Their slow swimming grants them resilience against poor maneuverability, allowing them to drift without stirring predators into chase, but their awareness is constant. A prowling moray eel passes nearby, its sinuous form casting a moving shadow. The puffer reacts subtly. Slight fin adjustments, a pause in motion, a calculation of distance and likelihood. It does not inflate. It does not need to. The eel carries enough evolutionary memory to leave the fish undisturbed. Further along the reef, juvenile puffers navigate shallow nurseries. Their small size makes them vulnerable, yet predators often ignore them, deterred by their developing toxicity. Young puffers cannot inflate fully, but even at this stage their tissues contain mild doses of tetrodotoxin. These juveniles feed on a diet that introduces the toxin-producing bacteria into their bodies, gradually building their chemical defense. The process demonstrates that toxicity in puffers is not static, but accumulative, shaped by diet and microbial partnerships. The fish are, in essence, cultivating their own defense system with every meal. The puffer's inflating mechanism carries physiological risks. Inflating repeatedly can strain the stomach lining, and the energy expenditure required to return to normal size is significant. After deflating, puffers expel water and rest to recover. During this period, they're at their most vulnerable. A tired puffer cannot swim effectively or employ its full defense. Therefore, puffers avoid inflating unless absolutely necessary. Evolution rarely selects for wasteful strategies, and inflation remains a last resort rather than a casual habit. As the sun lowers in the sky, the lagoon shifts into evening hues. The water becomes a canvas of deep blues and golds. Many daytime predators retreat, replaced by nocturnal hunters that rely more on scent and vibration than vision. Under these changing conditions, the puffer moves to sheltered areas. Unlike fast-moving fish that race into crevices, the puffer casually explores until it finds a patch of sand or a coral overhang that promises safety. It beds down with steady movements, maintaining enough awareness to detect approaching danger. Night reveals another side of the puffer's relationship with the ecosystem. Some puffers emit chemical cues that deter nocturnal predators from approaching. Others use the cover of darkness to forage more freely, consuming benthic organisms that become active at dusk. Even here, the puffer moves with the same quirky, gentle rhythm that has made it appear almost harmless to human observers. This contrast between appearance and potency underscores the strange duality of the species. It is a creature that looks fragile, but carries one of the deadliest cocktails in the natural world. As the lagoon grows still, tiny bioluminescent particles drift upward, creating a starfield effect along the seafloor. The puffer, nestled quietly beneath a coral ledge, becomes part of the landscape. Nothing about it hints at the violent reactions its toxin can induce. Nothing reveals the extreme contingency plan waiting behind its seemingly gentle exterior. Yet its survival depends on this combination of innocence and threat. In a world full of predators with teeth, speed, and cunning, the puffer remains protected by biology's most unforgettable contradiction. A soft, awkward balloon filled with enough poison to rewrite the food chain. The chapter closes on this paradox. The fish's silhouette fades into the blue as the currents slow. It is a reminder that in nature, danger does not always announce itself with claws or fangs. Sometimes, it arrives disguised as a harmless little sphere drifting peacefully through the reef, a creature defined not by pursuit or aggression, but by the quiet, unwavering logic of survival through deterrence. The puffer is a mutant of its own making, shaped by evolution into something simultaneously adorable and apocalyptic, a floating warning that beauty and lethality sometimes share the same gentle smile. The shoreline appears calm in the early hours, long before swimmers disturb the surface with splashes and laughter. Pale sunlight glides across the shallows, turning the water into a pane of trembling glass. Beneath it, the world wakes slowly. Sand ripples formed by last night's tide stretch into gentle waves. Tiny fish hover where the light is strongest, using the soft illumination to forage. Nothing suggests danger. And yet danger drifts here, almost imperceptible, suspended in water so clear that the threat remains hidden until it is already too close. A faint shimmer breaks the surface reflection. At first it resembles a transparent plastic bag caught in a lazy current, folding and unfolding with the swell. But the symmetry is too perfect, the edges too sharply defined when sunlight bends just right. A box jellyfish floats just meters from the beach, its cube-shaped bell sculpted so precisely that it looks designed rather than grown. The creature is nearly invisible, a geometry of death carried by the tide. From the corners of the bell trail dozens of tentacles, each one thin as a thread and extending farther than the length of a large bus when fully deployed. They drift behind the jellyfish with a deceptively peaceful grace, swaying like strands of silk in slow motion. But every centimeter of these tentacles houses dense clusters of nematocysts, stinging cells armed with microscopic harpoons. These barbs fire upon the slightest touch, injecting venom so potent that it can stop a human heart in minutes. Predators do not learn to avoid box jellies through trial and error. They avoid them because the ocean rarely gives a second chance to those who make contact. As the camera moves closer, the jellyfish's cube-shaped bell reveals its true complexity. Each of the four sides contains clusters of eyes, grouped in sets called rhopalia. In total, the box jellyfish carries dozens of visual organs. Some detect shadows, others detect brightness, and a few, remarkably, possess lenses capable of forming images. These sophisticated eyes allow the jellyfish to navigate, avoid obstacles, and orient itself toward habitat features, a feat that contradicts the common perception of jellyfish as mindless drifters. The box jellyfish swims with intention. Pulses of contraction travel rhythmically through the bell, guiding it along the coastline where small fish and crustaceans gather. The camera follows the jellyfish as it glides through a shallow cove. It adjusts its position when it approaches a rock. It rises when the seabed lifts. It turns slightly when the current carries debris. Everything about its movement is controlled. Unlike many jellyfish, which surrender to the ocean's flow, the box jellyfish actively steers. This control gives it access to hunting grounds unavailable to less maneuverable species. It slips into estuaries, mangrove channels, and beach shallows where juvenile fish congregate in dense schools. In the water column around the jellyfish, the world becomes a silent trap. Tiny fish weave in playful bursts, unaware of the danger. A few brush briefly against drifting tentacles. Instantaneously, the nematocysts fire. Each microscopic harpoon pierces the skin and injects venom that targets ion channels in nerve and muscle cells. The prey loses control of its muscles within seconds, spasming once before falling limp. The jellyfish retracts the tentacle, pulling the immobile prey toward the bell. Digestion begins externally as enzymes diffuse into the captured fish, breaking tissues down into a nutrient-rich slurry absorbed directly across the jellyfish's surfaces. It is a feeding strategy devoid of drama, efficient, silent, and devastating. The venom of a box jellyfish is one of the fastest-acting toxins known in the marine world. In humans, it can induce intense pain, cardiovascular collapse, and respiratory failure. The most lethal species, such as those found in the Indo-Pacific, are capable of delivering enough venom in a single encounter to kill multiple adult humans. The venom evolved not for large animals, but for the rapid capture of agile prey. Fish reflexes are blindingly fast, and only a toxin that disables nerves almost instantly can ensure success. Humans, with much slower reaction times, suffer catastrophic consequences simply because the venom works too efficiently on their physiology. Despite its lethality, the box jellyfish remains fragile. Its body is composed mostly of water, its tissues as delicate as wet tissue paper. A strong wave can tear its tentacles. A shift in salinity can damage its internal balance. But fragility in structure does not equate fragility in design. The jellyfish's transparency evolved in tandem with its venom, creating a predator that hunts by erasing its own presence. A fish scanning its environment for threats looks for silhouettes, contrasts, movement patterns. The jellyfish offers none of these cues. Even its tentacles can remain nearly invisible, refracting light rather than blocking it. Only when sunlight hits the bell at a precise angle does the structure reveal itself as a ghostly cube drifting in the tide. The camera follows the jellyfish deeper into the cove. Mangrove roots rise like pillars from the sandy floor, each one coated in algae and encrusting organisms. Juvenile fish cluster around the roots, darting in tight, synchronized pulses whenever a shadow crosses their path. The jellyfish enters slowly, sensing prey density through subtle changes in water chemistry and light distortions. Its tentacles spread wider, forming a lethal curtain 10 meters across. Fish that drift too close are struck by an invisible net of venom. One moment they flick along the roots, the next they freeze mid-swim, bodies suddenly rigid. The jellyfish reels them in without altering its slow, drifting gait. What makes this scene even more remarkable is how the jellyfish navigates this complex landscape without entangling its own tentacles. The Rhopalia, each containing several eye types, provide depth cues and spatial orientation. The eyes do not function like human eyes. They interpret patterns of light that reveal edges, shapes, and movement. The jellyfish uses this information to adjust the pulse pattern of its bell, maintaining central alignment within tight spaces. Its movement lacks elegance, yet the precision is undeniable. The animal simply avoids touching objects, even when surrounded by them. As midday approaches, the water warms and currents intensify. This shift influences the box jellyfish's behavior. Warmer waters raise metabolic rates, which can increase hunting activity. The jellyfish drifts toward open water, where tidal pulses carry planktonic organisms and juvenile fish offshore. Here, its tentacles extend to their full length, creating a capture zone so vast that few prey can escape by accident alone. The jellyfish positions itself along the current, allowing water to flow past its tentacles while it remains nearly motionless. This passive hunting strategy conserves energy, ideal for an animal with no centralized brain to coordinate complex movement. And yet the jellyfish does maintain a form of central processing. A nerve ring around the bell coordinates signals from the Rhopalia, adjusting pulsation rate and tentacle deployment. Though primitive by vertebrate standards, this neural system gives the jellyfish remarkable adaptability. It can speed up when currents threaten to push it into shallow surf. It can slow down to hover above a sandy patch teeming with prey. It can even orient itself toward reflective surfaces in low-light conditions. As the sun begins to lower, swimmers often enter the water unaware of the box jellyfish's presence. Turbid evening light makes the creature even harder to detect. Its bell blends seamlessly into the dimming environment, and its tentacles become indistinguishable from the swaying particles in the water column. A human leg brushing against a tentacle receives dozens, sometimes hundreds of stings simultaneously. Pain erupts instantly, described by survivors as burning metal pressed against the skin. Red welts spread in ladder-like patterns. Without rapid medical intervention, the venom begins affecting the heart and respiratory muscles. In severe cases, the victim collapses within minutes. Despite the danger, Box jellyfish do not seek interaction with humans. They are not aggressive. They drift where currents take them, hunting fish and crustaceans in ecosystems that have shaped their biology for millions of years. Beaches and coastal developments have simply expanded into their habitat. Many coastal nations now deploy nets or monitoring systems to reduce encounters, yet sightings remain unpredictable. The ocean does not publish warnings, and the jellyfish offers none. As twilight spreads across the cove, the box jellyfish resumes its silent drift. Its tentacles retract slightly as it moves toward deeper water, where night currents will disperse it alongside many others of its kind. The camera lingers on the bell, watching the faint internal structures pulse gently with each contraction. It is a creature defined by contradiction, delicate but deadly, structureless yet precise, invisible yet unforgettable to those who have encountered it. The ocean is filled with predators that announce themselves with teeth, speed, and power. But this one survives by erasing the boundary between itself and the water, becoming a threat that is felt only after it is already too late. In the end, the box jellyfish stands as a reminder that simplicity in form can cloak extraordinary complexity. It is a drifting cube of transparency, carrying one of the most powerful chemical weapons on Earth, guided by eyes that see more than expected, and instincts shaped by a world where survival depends on perfecting the art of being unseen. Dawn lifts slowly over the reef, sending pale beams of sunlight downward through layers of clear tropical water. Suspended particles ignite briefly as the light touches them, turning the upper reef into a drifting constellation of tiny sparks. Coral outcrops glow with soft pastel hues, their polyps opening like thousands of miniature flowers reaching for the day's first light. Schools of small reef fish stir from their nighttime shelters, rising into the water column in shimmering clouds that flash silver and gold with each synchronized twist. Amid this gentle awakening, a shape emerges with such elegance that it seems almost sculpted. The lionfish glides into view, its long, ornate fins trailing behind like embroidered silk veils, drifting in a slow-motion current. Bands of cream, rust, and deep cinnamon stripe its body in perfect symmetry, creating a pattern that feels more like luxury fabric than evolutionary adaptation. From each fin ray extends a slender spine, stiff, sharp, and infused with venom. These spines radiate in all directions, transforming the lionfish into a floating crown of weaponry. It moves with the confident ease of a creature that knows very little in the reef can harm it. The lionfish's beauty is a form of biological misdirection. Coral reefs often rely on quick interpretation of visual cues. Bright colors typically warn of toxins, stripes break outlines, and exaggerated fins serve to intimidate. The lionfish combines all of these traits into a single form that looks more theatrical than threatening. Predators hesitate, uncertain whether the display is bluff or promise. The cost of testing the theory is high. A single sting from the lionfish's dorsal or pectoral spines delivers venom that causes intense pain, swelling, and in extreme cases, systemic complications. For large predators, the sting is rarely fatal, but the memory of it is enough to shape behavior for a lifetime. The lionfish's body advertises its danger with perfect honesty. Touch at your own risk. As the lionfish drifts through a narrow coral canyon, its movement appears lazy, almost indifferent. It does not dart or chase like other reef predators. Instead, it floats with slow, deliberate pulses of its pectoral fins, maintaining a steady hover just above the substrate. This slow movement is not a weakness, but a hunting tactic. Many small fish interpret sudden acceleration as threat, triggering escape reflexes. The lionfish offers none of that stimulus. It simply approaches in silence, spreading its broad fan-like fins outward to form a curved wall that shepherds prey into tighter spaces. The small fish find themselves boxed in by a living barrier that expands and contracts with calculated precision. In this underwater choreography, the lionfish becomes both shepherd and executioner. Once the prey are cornered, the lionfish shifts slightly, orienting its mouth toward the trapped fish. The final strike is shockingly fast. The lionfish inhales with explosive force, creating a suction vortex that pulls prey directly into its mouth before they can blink. The motion is over in a fraction of a second. The hovering resumes, serene and unhurried, as if the entire sequence required no more effort than a slow wave of the fin. This predatory behavior evolved in the Indo-Pacific, where reefs are vast and predator-prey interactions are shaped by centuries of complex ecological balance. But the lionfish's story took a catastrophic turn when the species entered the Atlantic Ocean, likely released by aquarium owners or transported accidentally. In the Atlantic, the lionfish encountered an ecosystem unprepared for its combination of elegance and ruthlessness. Native predators did not recognize its warning stripes. Native prey did not understand its slow, stalking approach. And the reefs themselves, already stressed by warming waters and pollution, did not have the resilience needed to absorb the impact of a new apex mesopredator. The camera transitions to an Atlantic reef, where the difference is striking. The coral appears more sparse. Patches of rubble interrupt healthy growth, and the density of juvenile fish is noticeably reduced. Lionfish hover in groups here, a behavior less common in their native range. Each one patrols a small territory, sweeping through seagrass beds and coral outcrops with the steady rhythm of a predator on an unchallenged march. Their stomachs swell visibly after feeding, often bulging with the silhouettes of multiple fish. Studies have shown that a single lionfish can reduce juvenile reef fish populations dramatically within a short period. Unlike many predators that specialize in particular prey species, lionfish exhibit an astonishingly broad diet, consuming dozens of species ranging from tiny damselfish to shrimp and small crustaceans. This indiscriminate feeding disrupts the ecological pyramid from the bottom up. Juvenile fish serve as grazers, cleaners, and filters for the reef. They maintain algae balance, support coral health, and act as prey for larger predators. Removing them destabilizes the entire structure. The lionfish's presence essentially accelerates the reef's collapse by removing its most vital workers. This unchecked predation is amplified by the lionfish's reproductive output. Females release gelatinous egg clusters that drift with the current, each containing tens of thousands of eggs. In warm waters, these eggs hatch quickly, allowing lionfish populations to explode. Their venomous spines protect them from predation, and their adaptable hunting strategy allows them to dominate landscapes far beyond their evolutionary origins. The camera returns to a lionfish navigating a section of reef enriched with open water and soft coral. Its eyes, positioned high on its head, scan the environment constantly. Unlike many fish with narrow binocular vision, lionfish see a broad field. This panoramic awareness helps them gauge prey movement and maintain perfect hovering control. The fish adjusts tiny muscles along its fin bases to balance itself with subtlety. It never seems rushed, even when hunting in strong currents. The body, with its exaggerated frills and delicate fins, appears delicate. But beneath that elegance lies a predator, perfectly adapted for ambush and control. Another layer of complexity emerges in their feeding mechanics. Lionfish can flare their gill covers outward, expanding their head profile and disorienting prey by altering water flow around them. This tactic works especially well in enclosed spaces such as crevices and coral alcoves. The fish effectively manipulates hydrodynamics to limit escape routes. What appears to be a slow, ornamental dance is in fact a series of precise calculations. Adjust fin position, manipulate current, constrict the escape corridor, strike. The venomous spines play a second role beyond defense. They create a visual illusion that makes the lionfish appear larger than its actual mass. Many prey species assess danger by estimating size. A predator that seems too large to evade triggers panic responses that lead to poor decision-making. Lionfish exploit this by shaping the psychological landscape of the water around them. The frills and stripes amplify their silhouette, turning them into looming figures capable of inducing confusion long before contact is made. The chapter shifts to night, when bioluminescent organisms shimmer along the reef. The lionfish, unlike many diurnal predators, remains active under low light. Its eyes adapt quickly, and its hunting strategy works just as effectively in darkness. Small plankton-feeding fish rise from their daytime shelters, becoming easy targets. The lionfish's hovering becomes more ghost-like, its fins trailing with the gentlest of oscillations. The elegance is even more pronounced at night, where the faint glimmer of moonlight along its spines resembles the flicker of a dangerous lantern. Invasive lionfish populations in the Atlantic have begun altering the nocturnal dynamic of reefs as well. Where once only native predators hunted in particular zones, lionfish now occupy those spaces with confidence. Their presence forces behavioral shifts in other species. Some prey no longer venture into open water at dusk. Some predators follow lionfish movements at a distance, hoping to scavenge leftovers. These cascading effects reveal the lionfish not only as a predator, but as a force that modifies the ecosystem's entire rhythm. Yet, despite the ecological damage and the danger posed by their venom, lionfish remain mesmerizingly beautiful. Their appearance is a contradiction, a biological paradox where aesthetics mask lethality. This contrast contributes to their popularity in aquariums, where they glide behind glass with the same effortless confidence. But in the wild, beauty becomes a weapon. Patterns serve to confuse and intimidate. Fins serve to trap. Venom serves to warn. And reproduction serves to expand their influence with relentless efficiency. The chapter closes with a return to the morning reef. A lionfish rises slowly from a cluster of coral heads, lit from behind by golden sunlight. Its fins spread into perfect radial symmetry, a living explosion of stripes and translucent rays. It hovers in absolute stillness, a portrait of grace suspended above a world it is steadily changing. The reef glitters around it, colorful and vibrant, yet increasingly vulnerable to the quiet plague drifting within it. In the end, the lionfish represents a lesson in ecological fragility, a designer predator that looks like art, but behaves like a spreading stain, consuming without hesitation and expanding without restraint. Beauty here is not decoration. It is a delivery system for dominance, a biohazard disguised as a masterpiece. At first glance, the seabed looks empty. A quiet sheet of sand stretches outward in every direction, punctuated only by scattered rubble and the occasional patch of seagrass stirred by the faintest of currents. Sunbeams fall onto the bottom in trembling columns, illuminating grains of crushed coral and casting flecks of gold across the landscape. Fish pass above with the lazy confidence of animals that believe they understand their surroundings. The seafloor appears harmless, even dull. Yet it is in this monotony that one of the ocean's most dangerous illusions waits, motionless and patient, sculpted by evolution into perfect deception. A grey, lumpy mass sits half buried among the sand and broken shells. It is indistinguishable from the stones surrounding it. The surface is irregular, covered with ridges, pits and tufts of algae that look like natural growths. Tiny crusts of sediment cling to its skin as though glued in place. Nothing about it suggests animation. Nothing indicates a predator with one of the most potent venom delivery systems on Earth. And yet, beneath the camouflage, a stonefish lies perfectly still, its body pressed against the substrate, its fins tucked tightly to minimize any hint of movement that might betray its presence. The stonefish's disguise is not merely visual. Its tissues integrate grains of sand, algal fragments, and organic debris into a semi-permanent texture, creating a surface that feels like rock to any creature that brushes against it. This tactile mimicry plays a crucial role in its survival, because predators and prey in shallow waters rely heavily on touch when visibility is reduced by turbidity or shifting light. A fish grazing near the bottom may graze across the stonefish without recognizing danger until it is too late. Even marine animals with excellent pattern recognition fail to distinguish the subtle, uneven lump from ordinary substrate. The camera closes in slowly, revealing the slightest of details. Two small eyes protruding from the top of the head, positioned upward to scan for silhouettes of passing prey. They do not blink, they do not shift. They simply observe with patient calculation. Stonefish are ambush predators, specialists in stillness, expending minimal energy until the exact moment of need. This strategy suits their physiology, which favors power over endurance, precision over pursuit. They do not chase. They do not chase because they do not need to. A small fish approaches. It hovers near the stony mass, nibbling at flakes of algae drifting by. The stonefish does not tremble. It does not coil like a spring. Its body remains entirely relaxed. Only when the prey crosses a narrow threshold, just centimeters from its mouth, does the transformation occur. The jaws open with explosive force, creating a vacuum that sucks the prey inward in less than a tenth of a second. The attack is so fast that water visibly distorts, forming a brief cavity that collapses with a ripple. The prey vanishes. The stonefish settles again, its mouth closing with a subtle click. The disturbance fades, and the illusion resets. Within moments, the stonefish appears once more, like an inert object left behind by the tide. But it is not the stonefish's predatory success that earns it its notorious reputation. It is the defense, the venomous spines protruding from its dorsal ridge. These spines lie mostly concealed when the fish is at rest, appearing as irregular bumps among the algae-laden camouflage. Yet each one is connected to a venom gland capable of delivering a dose of toxin that causes searing pain, swelling, tissue damage, and in extreme cases, cardiovascular failure. The venom evolved not for hunting, but for discouraging predators. The stonefish's inability to flee makes defense essential. Any creature that attempts to swallow or bite it receives a life-altering lesson. In the shallow waters where humans often wander barefoot, the risk becomes an accidental consequence of the stonefish's perfect mimicry. When stepped on, the stonefish cannot avoid contact. Instead, the dorsal spines rise reflexively, piercing through skin or neoprene with ease. The pressure of the foot forces the venom sac to compress, injecting the toxin deep into tissue. Victims often describe the pain as immediate and overwhelming, radiating through the limb with waves of intense burning. The venom attacks not only sensory nerves, but also the cardiovascular system, triggering dangerous shifts in heart rhythm and blood pressure. The injury site swells rapidly. Without rapid treatment, the effects can progress to paralysis or collapse. In regions where stonefish are common, warning signs dot beaches, reminding visitors that the most dangerous creatures are often the ones they cannot see. The stonefish's venom composition is a system refined through evolutionary arms races. Proteins known as stoneostoxins create pores in cell membranes, causing rapid fluid imbalance and intense inflammation. Other components trigger nerve responses that amplify the perception of pain far beyond normal thresholds. Interestingly, the venom appears fundamentally defensive. Stonefish rarely use it in hunting, as their suction-feeding strike is efficient enough to handle prey without venom. This separation of offensive and defensive strategies reveals a careful balance. The energy cost of producing venom is high, so the stonefish deploys it only under threat. The environment shapes its behavior further. Stonefish inhabit shallows, estuaries, and coral rubble, areas where predators such as sharks and rays patrol frequently. Many predators rely on crushing jaws to break hard-shelled prey. A fish that resembles a rock invites an exploratory bite from such predators, and without venom, the stonefish would not survive long. The spines serve as a potent deterrent. A single failed attempt by a predator leaves a lasting impression, reducing the chance of future attacks on any stonefish in the area. In this way, individual encounters shape ecological memory across entire communities of reef animals. The chapter shifts to a stormier scene. Clouds gather overhead, darkening the water. Waves churn sediment, reducing visibility. These conditions highlight the stonefish's advantage. While many fish flee turbulence, the stonefish thrives in uncertainty. Suspended particles increase its invisibility, and prey become easier to ambush as they struggle against the shifting currents. Humans wading through murky shallows may find themselves dangerously close without realizing it. The accidental nature of stonefish stings reflects not aggression, but unfortunate proximity. The fish possesses no interest in contact, only survival. A new behavior emerges as the camera follows a stonefish moving across the sandy bottom. Though often described as sedentary, stonefish do relocate when necessary, particularly for feeding or reproduction. Their movement is slow and awkward, more of a glide than a swim, with their large pectoral fins functioning as stabilizing supports. They ease themselves over obstacles without breaking the illusion of rock-like stillness. Even in motion, the camouflage holds. Their colors shift subtly as they settle into new surroundings, adjusting to match the hue and grain size of the substrate. Stonefish reproduction remains largely hidden, occurring beneath sand or within coral crevices. Females release eggs into shallow depressions where males fertilize them externally. The young hatch into larvae that drift with the plankton, carried by tides far from the bottom-dwelling habits of adults. Only after metamorphosis do they settle onto the substrate, beginning the slow process of acquiring the camouflage and adult shape that defines their survival. In these early months, the juveniles rely on rapid color changes to blend with the environment. Their venom glands form quickly, providing protection even at small sizes. Night falls across the reef. Bioluminescent organisms flicker faintly in the current. Under this dim light, the stonefish becomes even harder to distinguish. Its outline merges with the shadows cast by coral rubble. Only the faint rhythmic expansion of its gills betrays life. Small nocturnal crustaceans scuttle nearby, unaware that their path leads through the strike zone of a predator adapted for darkness. The stonefish, despite its immobility, senses pressure changes in the water. A slight shift, just enough to suggest a passing crab, triggers the lightning-fast expansion of its mouth. The strike succeeds. The stonefish returns to stillness, its meal swallowed whole. As the tide retreats, leaving stretches of reef exposed, the stonefish remains submerged in tidal pools. These pools are risky environments, subject to rapid temperature shifts and changes in salinity. Yet stonefish endure through physiological tolerance and behavioral adjustment. They burrow shallowly into the substrate, minimizing exposure and using low metabolic rates to withstand fluctuations. Their resilience makes them formidable survivors, able to outlast disruptions that might kill less adaptable species. The chapter closes with a final image, a stonefish resting beneath the morning light as a human swimmer approaches the shallows. The fish does not move, it does not flare its spines, it does not warn, it simply waits. A perfect rock among rocks, the danger lies not in hostility, but in invisibility. This is the ultimate do not step there mutation. A predator perfected by stillness, armored by venom, and hidden within the very fabric of the seafloor. In nature, fear often comes from what can be seen, the flash of teeth, the speed of a chase, the silhouette of a hunter. But the stonefish teaches a more unsettling lesson. Sometimes the most dangerous organism is the one that looks like nothing at all. In the dim blue of early morning, the kelp forest sways like an underwater cathedral. Tall fronds rise from the seafloor toward the sunlit surface, their blades rippling in long, rhythmic arcs as currents push through the forest's corridors. Schools of fish weave between the pillars of kelp, scattering silver sparks through the gloom. Small crustaceans crawl along the stipes, picking at films of algae that grow in delicate patterns. The forest feels alive in every direction, towering, sheltering, dense. Yet beneath this lush canopy lies a quiet pressure that does not rise quickly or violently, but instead gnaws steadily, grain by grain, wearing the forest down from its roots. On a patch of rock mottled by shadows, a sea urchin clings tightly with dozens of tube feet that grip as delicately as fingertips and as firmly as anchors. Its spines bristle outward, long dark needles arranged in concentric patterns. At first glance, the creature looks more like a fallen seed pod or a drifting piece of debris than a living animal. But then the urchin shifts slightly, rotating its body with the slow, methodical precision of a machine built for patience. Below the spines, a circular mouth opens and closes rhythmically, equipped with 5 calcified teeth arranged in a structure known as Aristotle's lantern. These teeth do not merely nibble, they scrape, they rasp, they carve away tiny fragments of rock and algae, wearing down the substrate grain by grain. The scraping sound is almost imperceptible. It echoes faintly as the urchin grinds across the rocky surface, feeding on whatever organic matter it can reach. In the process, the creature performs a geological act, eroding stone into sediment. This contribution is slow but relentless. Over decades, the collective feeding of countless urchins reshapes the seabed, contributing fine sand to reefs and altering contours of the coastline. Yet this is only one side of their role. In kelp forests, the bite of an urchin carries far greater consequence. The camera drifts upward, following a kelp stipe as it rises toward the light. At its base lies a holdfast, a tightly knotted mass of root-like structures woven around the rocks. It is from here that the kelp's entire structure draws support. Around the holdfast, several sea urchins gather. They position themselves as if circling a fallen tree, each one scraping slowly where the holdfast meets the substrate. The kelp's immense body sways above them, still vibrant, still gathering sunlight, but the attack occurs at its foundation. The urchins scrape and scrape until the holdfast weakens. When a particularly strong current passes through, the kelp breaks free. It floats upward like a severed limb. The forest loses another pillar. In healthy ecosystems, predators keep urchin populations in check. Sea otters patrol the kelp forests, prying urchins from rocks with nimble paws and devouring them with astonishing appetite. Large fish such as triggerfish and sheephead crack open urchins with specialized jaws. These predators maintain balance by ensuring that grazing pressure does not exceed what the kelp forest can recover from. But when these predators disappear, removed by overfishing, hunted for fur, or pushed aside by environmental disruption, the urchins proliferate unchecked. What begins as a natural grazing pattern transforms into an ecological crisis. Where once the forest stood tall and dense, now lies an urchin barren, a desolate landscape littered with the pale skeletons of corals and kelp roots. The seafloor becomes a monochrome desert of spines and rock. Thousands of urchins spread across the terrain like a slow-moving army of armored grazers. Without kelp to shade the water, sunlight penetrates deeper, altering temperature patterns and promoting the growth of turf algae. Fish that depended on the kelp forest for shelter vanish. Crustaceans lose their protective corridors. Even the microbial life shifts, responding to the changed nutrient cycles. A forest that once sheltered hundreds of species now supports a fraction of its former richness. The camera moves through one of these barrens. It feels abandoned, quiet in a way that suggests not peace but loss. The only movement comes from the spines of the urchins, twitching in slow, rhythmic sequences as the animals reposition themselves. Their tube feet extend and contract in translucent waves, gripping rocks with suction cups so delicate they can grasp a single grain of sand. Their colors vary, purple, red, black, depending on the species and region. Despite their spiny appearance, urchins are sensitive creatures, responding to changes in light and water chemistry with surprising precision. But sensitivity alone does not prevent devastation. It is the imbalance, not the organism, that creates the wasteland. Some species of sea urchin carry additional defenses beyond their spines. The flower urchin, for example, bears venomous pedicellariae, small clamp-like structures that deliver potent toxins when they latch onto skin. These toxins can cause paralysis, hallucinations, or intense pain. The fire urchin combines vibrant coloration with venomous spines that release neurotoxins upon contact, a warning painted boldly across its body. Even species considered harmless can cause injury when stepped upon, as their spines break easily and embed themselves deeply in flesh. The idea of danger from something so slow-moving feels counterintuitive. Yet these organisms occupy an important niche in the ecosystem, wielding their chemical defenses like silent reminders that not all hazards rush or strike. Some simply wait. The narrative shifts to a reef crest where predators still thrive. Here, a lone sheephead fish approaches an urchin resting on a boulder. It circles the spiny orb, evaluating. The sheephead knows exactly where to strike, directly on the underside where the spines are shortest. With a sharp snap of its jaws, it crushes the urchin's shell, sending fragments spinning through the water. The predation is swift and decisive. For ecosystems where such predators still exist in abundance, urchin populations remain balanced and kelp forests flourish. But human interference often disrupts this balance. In some regions, the removal of predator species has allowed urchins to multiply beyond the carrying capacity of the environment. Warmer oceans also accelerate urchin metabolism and reproduction, enabling them to graze faster and farther. Together, these forces create runaway feedback loops. The more the kelp disappears, the fewer fish remain. The fewer fish remain, the less control there is over urchin populations. The barren expands, and recovery becomes increasingly difficult. Yet urchins also reveal the resilience of ecosystems when balance is restored. In areas where predators have been reintroduced, such as the re-establishment of sea otters in parts of the northeastern Pacific, kelp forests have begun to rebound dramatically. Otters consume urchins regularly, reducing their numbers and driving survivors into crevices where they cannot access kelp holdfasts. With grazing pressure reduced, kelp regrows, bringing back fish, invertebrates, and entire underwater communities. This transformation demonstrates the interconnectedness of even the smallest grazing organisms and the largest predators. Returning to the seafloor, the camera observes an individual urchin navigating across a field of rubble. Its spines flex in coordinated waves, moving not randomly but in patterns dictated by tiny muscles that adjust each spine's orientation. Beneath the spines, the tube feet extend outward, probing the surface with delicate tips that detect chemical signatures and changes in pressure. The urchin navigates not by seeing, its vision is limited to detecting light and shadow, but by sensing gradients of texture, scent, and current. Its world is built from close-range perception, yet this is enough to shape entire landscapes. The urchin pauses beside a patch of encrusting algae. Its teeth extend again, scraping with such persistence that faint grooves appear in the stone. These teeth, made of calcite reinforced with magnesium, are among the most durable biological tools found in marine environments. They sharpen continuously as the outermost layers erode through use, revealing fresh, sharp edges beneath. Scientists have studied the structure of urchin teeth as models for designing abrasion-resistant materials. Evolution, through countless generations, refined them to endure constant grinding. As daylight deepens and shadows shift, the kelp forest above whispers in long, rolling movements initiated by the changing tide. In barrens, those whispers fall silent. The contrast is stark, a reminder of how quickly ecological roles can transform when balance is disrupted. Urchins are not villains. They are participants in a system that depends on checks and counterbalances. Their grazing is essential in moderation, harmful in excess, and catastrophic when released from natural constraint. Their spines, though intimidating, are defenses shaped by a world filled with predators eager for a nutrient-dense meal. Their ability to strip landscapes bare is not malice but adaptation, a survival strategy that becomes destructive only when predators vanish. The chapter ends with a quiet view of an urchin resting in a tide pool, the water rippling gently around its spines as the sun sets. Around it lie fragments of stone it has scraped away, the beginnings of sediment grains that will someday contribute to beaches, reef structures, or ocean floors far from this pool. Even in the smallest interactions, the urchin participates in geological and ecological processes that stretch beyond its spiny shape. It is a creature defined by slow persistence, steady hunger, and surprising influence. A reminder that transformation in nature does not always require speed or violence. Sometimes it comes from the simple, relentless scraping of teeth against rock, reshaping worlds one grain at a time. The coastal shallows glow with the first amber light of morning, illuminating a world that seems more like a drifting meadow than a marine habitat. Seagrass blades sway in slow arcs, rising from the sandy seabed like slender green ribbons pulled by the tide. Tiny bubbles cling to their edges, sparkling as the sunlight slips past. Small crustaceans hop between the leaves with delicate, twitching legs. A few juvenile fish weave uncertain paths through the maze, their movements jittery and instinctive. Nothing about this tranquil landscape hints at one of evolution's strangest experiments. A creature shaped like a scrap of myth, built with a vertical spine in a horizontal world, and governed by a reproductive script that rewrites the rules of parenthood. Near the base of a swaying frond, a seahorse clings with the curled end of its tail wrapped around a stem. It hangs there like a tiny ornament, hardly moving, except for the faint sway of its body, mirroring the rhythm of the surrounding grass. The shape is unmistakable. Horse-like head with a long snout, armored torso with bony plates arranged in ringed segments, a neck that arches with almost mammalian grace. But this is no miniature horse, no wandering relic. It is a fish, albeit one that seems to have ignored every guideline for what a fish should look like. Unlike most fish that rely on streamlined bodies to dart through open water, the seahorse has adopted a fully upright stance. It faces forward, its head held high, its back straight. This vertical posture gives it the appearance of standing more than swimming. The tail, prehensile and muscular, anchors the body to vegetation and provides stability. Instead of fins built for speed, the seahorse uses a diminutive dorsal fin that beats at high frequency to push itself forward with gentle pulses. Two tiny pectoral fins act as subtle rudders. The result is movement that appears nearly weightless, a drifting ballet rather than purposeful travel. Predator avoidance relies not on escape, but invisibility. Camouflage is essential here. Seahorses grow skin filaments and irregular bumps that match the texture of surrounding plants. They shift between earthy yellows, muted greens, rusty browns, and even pale reds. They are observers rather than explorers, choosing vantage points where the world moves around them and not the other way around. Their eyes, able to swivel independently, scan for threats and opportunities in different directions simultaneously. One eye may track a shrimp inching closer, the other monitors a distant fish. Their perception of the world is panoramic and precise. Hunting for a seahorse is an exercise in patience and physics. Their lack of speed could have doomed them, but evolution solved the problem in an elegant way. Seahorses are ambush predators. They remain still until prey comes close, sometimes within only a few millimeters. When the moment is right, the seahorse strikes with a suction-feeding mechanism so rapid that it borders on imperceptible. The long snout acts as a pressure chamber. With a sudden expansion of the mouth cavity, water rushes inward, carrying the prey directly into the seahorse's throat. The strike lasts only milliseconds, faster than most fish can react. Shrimp, copepods, and larvae disappear in tiny gusts of water, vanishing before they realize they are in danger. For a creature that barely moves, the hunting strategy is remarkably effective. These suction strikes require precision. Seahorses have evolved a unique cranial joint system that allows them to pivot the head upward in an instant. Muscles contract, the snout snaps forward, and the vacuum pulls prey inward. Scientists refer to this as pivot feeding, a mechanism that maximizes acceleration over a short distance. The physics is so refined that seahorses have some of the highest strike success rates of any animal their size. They do not pursue prey, they do not chase. They merely wait, blending seamlessly with the grass until the exact moment arrives. But the seahorse's strangest story unfolds not in its hunting methods, but in its reproductive strategy. A reversal so profound that it stands nearly alone in the animal kingdom. Here, in these waving meadows, pregnancy belongs not to the females, but to the males. The transformation begins with a courtship dance. Two seahorses drift toward each other, mirroring movements in slow, deliberate synchrony. Their tails may intertwine briefly. Their bodies rise and fall with the tide's gentle pull. They display shifting colors, subtle pulses of light and pattern running along their plates. This dance establishes pair bonding, which can last for a season, or in some species, much longer. When the female is ready, she deposits her eggs into the male's brood pouch, a specialized chamber located on his abdomen. This pouch is not merely a container, it is a biological incubator. Upon receiving the eggs, the male fertilizes them internally and begins a complex physiological process of nurturing. The pouch regulates salinity, oxygen, temperature, and nutrients, creating an environment far more controlled than the external water column. Blood vessels proliferate, providing oxygen to developing embryos. The male seahorse becomes, in every functional way, the gestating parent. The sight of a pregnant male drifting through the seagrass forest is quietly extraordinary. His abdomen swells into a rounded globe. Inside, hundreds of tiny seahorses develop simultaneously, each coiled neatly in miniature form. They grow armored plates, curled tails, tiny snouts. By the time birth arrives, they are fully formed, independent and capable, though fragile. The male experiences rhythmic contractions, and in a dramatic burst, he expels the newborn seahorses from the pouch. They shoot outward like tiny sparks, propelled into the open water. Some births involve only a few dozen offspring. Others release well over 1,000. The newborns scatter instantly. There is no parental protection beyond this moment. They drift with the currents, carried into the world with nothing but instinct to guide them. Many will not survive. Predators collect them by the mouthful. only a small fraction will reach adulthood. This high-output reproduction ensures that seahorse populations persist despite vulnerability at every stage. The father, having completed his unusual role, rests briefly before preparing for the next breeding cycle. But the seahorse's evolutionary brilliance also makes it fragile. Its dependence on seagrass meadows and coral rubble creates vulnerability in a world where coastal habitats are disappearing. Pollution, trawling, and sediment disturbance reduce the places where seahorses can anchor and hide. Many species are now threatened, partly because of habitat loss and partly due to human demand. Seahorses are collected for aquariums, for traditional medicine, and as bycatch. Their slow movement and camouflage, once perfect survival tools, offer little protection against nets. In ecosystems where seahorses remain abundant, they play subtle yet important roles. Their grazing on small crustaceans helps regulate planktonic species. Their presence reflects ecosystem health. Thriving seahorses indicate thriving seagrass. Their reproductive cycle influences local nutrient flows as their brood pouch processes metabolic waste differently from other fish. And their existence reminds us how evolution can rewrite rules with startling creativity. The camera drifts downward to a seahorse resting near the sandy bottom. Its body mirrors the mottled pattern of the substrate. It grips a twig with its tail, anchoring against a light surge. A shrimp hovers nearby, unaware of the danger. The seahorse's head tilts ever so slightly. Then, with a rapid inhalation, the suction strike occurs. A tiny puff of silt rises. The shrimp is gone. The seahorse resumes its patient posture, swaying in unison with the grass, as if nothing has happened. Even the skeleton of the seahorse reflects its unconventional nature. Instead of flexible scales, its body is encased in bony rings that form a kind of armor, protecting it from many predators that would otherwise crush fish of similar size. This rigid frame, combined with poor swimming ability, forces the seahorse to rely entirely on stealth and habitat. Every part of its anatomy tells the story of a creature that has chosen an evolutionary path of specialization. It is not built to chase. It is not built to flee. It is built to blend. As the sun sets over the seagrass meadow, the water darkens into gradients of violet and charcoal. Shadows stretch across the sandy floor. The seahorse tightens its tail around its anchor point, reducing movement as predators emerge from crevices. Night is dangerous for slow-moving animals, but the seahorse's design remains its salvation. It appears now as little more than a tangle of plant matter caught in the dim current, a drifting scrap that predators overlook. In the fading light, the seahorse's silhouette becomes iconic. The curled tail, the bent neck, the slender snout. It looks like a creature drafted from imagination, but every feature reflects adaptation layered through millions of years. A fish that abandoned the fish blueprint, a father who carries the pregnancy, a hunter who catches prey without chasing it, a symbol of fragility and resilience balanced in one improbable form. The chapter ends with the camera rising slowly, leaving the seahorse swaying quietly among the grass. The meadow glows softly in the dusk. Little movements ripple through the vegetation, hints of life continuing in calm persistence. Somewhere within that gentle motion, another male may already be nurturing a brood, preparing to release hundreds of perfectly formed miniature seahorses into the world. The seahorse is not simply unusual. It is a reminder of nature's willingness to reinvent itself, rewriting expectations and overturning assumptions with every careful beat of its tiny fins. The reef glows like a mosaic under late morning sun, each coral colony catching the light in its own palette of soft pinks, bright oranges, fading greens and deep violets. Small fish flicker between branches like sparks, and the gentle hum of life, water pushing grains of sand, distant parrotfish scraping rock, the whisper of tidal pool, creates a soundscape so subtle it feels more imagined than heard. Yet in a shallow section of this reef, where currents swirl nutrients into a sheltered pocket, sits one of nature's most improbable fortresses, an anemone. Its tentacles sway softly, as though beckoning, each one tipped with stinging cells strong enough to paralyze most small creatures that dare to touch it. The anemone looks less like a plant and more like a slow-moving explosion of color, its body undulating in the water as if breathing through each tendril. Hovering just above the tentacles is a clownfish, bright orange, striped in bold white bands outlined in stark black. It hangs in the water with absolute confidence, as if the deadly anemone beneath it were nothing more than a garden cushion. The fish darts downward, brushing its side gently against the waving tentacles. Nothing happens. No sting, no shock, no paralysis. It is a private sanctuary, available only to those who possess the biological permissions encoded by evolution. The clownfish's immunity to the anemone's toxins is a delicate arrangement engineered through behavior and chemistry, working in perfect synchrony. When a clownfish first approaches an anemone, it does not rush in. It performs a slow, careful initiation ritual. The fish brushes lightly against the tentacles, backs away, returns, repeats, each touch transferring a little more mucus from its own body to the anemone's surface. Over time, the clownfish's mucus coat becomes saturated with chemicals that match the anemone's own signature. The anemone, which relies on chemical recognition to determine friend from foe, accepts the clownfish as part of itself. The stinging cells remain silent. The clownfish is granted immunity not through brute resistance, but through impersonation, a molecular disguise that nature perfected over countless generations. This immunity grants the clownfish access to one of the safest real estate properties on the reef. Predators avoid anemones. Tentacles mean risk. Yet for the clownfish, this fortress becomes a base of operations. It sleeps there, feeds nearby, reproduces inside its protection, and uses the anemone as a henchman in the complex territorial politics of reef life. The anemone provides sanctuary. The clownfish provides cleaning, nutrients, and defense against nibbling fish. It is symbiosis shaped into a partnership of necessity. Within this fortress lies a strict social hierarchy. A single dominant female rules the anemone, growing larger than all the others. She is unmistakable, usually the largest individual, bold in movement, and quick to assert control over her companions. Below her stands the breeding male, typically the second largest fish, who remains close at her side. Beneath them exists a lineup of smaller males called subordinates, functioning as an insurance policy for the stability of the group. This structure is not loose or optional. It is highly ordered, maintained by constant behavioral policing and by the biology of sex transformation itself. If the dominant female dies or is removed from the anemone, something extraordinary happens. The breeding male begins a process of complete sexual transformation. His gonads restructure, hormone levels shift, the male becomes female. Within days or weeks, depending on species and environmental conditions, the transformation completes. This newly formed female then ascends to leadership, assuming control over the anemone's territory. Meanwhile, one of the subordinate males, usually the largest, moves into the breeding male position. Reproductive roles cascade downward like a biological relay race. This system ensures that the anemone always has a breeding pair ready to continue the lineage, eliminating the vulnerability many species face when one reproductive individual dies. The camera lingers on the anemone as waves pulse overhead. The tentacles twist slightly with each current, creating a moving labyrinth. The clownfish weave in and out of this maze with surprising agility. Their small fins flutter constantly, allowing tight turns and sudden bursts of speed. Every motion reflects caution balanced with confidence. They never stray far from the safety of the tentacles. Yet within that safety, a complex web of relationships plays out. Subordinates maintain polite distance from the dominant female, avoiding direct challenges. Should one grow too quickly or behave too boldly, the female may bully it into submission, reducing its growth rate through stress-induced changes. This aggression maintains social order. The stability of the group depends on clear, uncontested hierarchy. The breeding cycle within this system is equally intricate. When the female is ready to lay eggs, she selects a flat surface near the base of the anemone, a rock or piece of coral sheltered by tentacles. She prepares the site meticulously by pecking away debris and cleaning it. Once she lays the eggs, the breeding male takes over as primary caregiver. He fans them with his fins to ensure proper oxygen flow, removes dead or infected eggs, and guards the nest with tireless dedication. This reversal, the female producing eggs and the male handling most parental duties, mirrors the broader theme of fluidity inherent to clownfish biology. Meanwhile, The anemone benefits from this vibrant activity. The clownfish's constant movement increases water circulation around its tentacles, improving oxygen delivery. Their waste provides nitrogen that nourishes the symbiotic algae living within the anemone's tissues. And when butterfly fish or other predators approach to nibble at the anemone, the clownfish lunges outward aggressively, nipping and chasing intruders away. In many ecosystems, an anemone with clownfish is significantly healthier and more vigorous than one without. This partnership elevates both species. The chemical dimension of this relationship adds further intrigue. The clownfish's mucus coat differs markedly from that of other fish. It lacks certain compounds that trigger nematocyst discharge. Instead, its mucus carries molecules resembling those of the anemone. This mimicry is not just camouflage, it is chemical diplomacy. The anemone essentially treats the clownfish as part of its own body. Science still debates the precise mechanisms, whether behavior primes the response, whether genetics encode the mimicry, or whether microbial partners on the fish's skin contribute to the process. What is certain is that clownfish walk a fine line. One error in mucus composition could render them vulnerable to the very tentacles they call home. Beyond this intimate chemical alliance lies the ecological role clownfish fill in reefs. They consume plankton, algae, and small invertebrates, helping maintain microbial balance around the anemone's tentacles. They attract predators, which inadvertently stimulate the anemone's feeding response. They even remove parasites that would otherwise weaken their host. The anemone is not a passive landlord. It benefits in measurable ways from its tenants. This reciprocity highlights the complexity of reef ecosystems, where survival depends not only on anatomy and skill, but on the delicate weaving of species into stable networks. The camera pans outward, revealing multiple anemones scattered across the terrain. Each hosts its own clan of clownfish, each with a dominant female, a breeding male, and several hopeful subordinates waiting for their chance at ascendance. The anemones sway in the gentle surge, their tentacles creating a rippling forest of soft, poisonous branches. Among them, clownfish dart like glowing embers. A reef that seems chaotic at a glance reveals an underlying architecture of roles, alliances, threats, and opportunities. Yet this equilibrium is fragile. Climate change threatens coral reefs, bleaching anemones, and disrupting the delicate habitats clownfish require. Warmer waters alter the chemical cues that clownfish rely on to recognize their homes. Ocean acidification affects the development of larvae, hindering their ability to locate suitable anemones. Human collection for aquariums removes individuals from ecosystems that depend on stable social structures. A single removal can unravel the hierarchy, triggering transformations that strain the group's stability. And yet, the clownfish endure, resilient through their adaptability. Their ability to change sex ensures reproductive continuity even when populations shrink. Their chemical masking protects them in landscapes thick with predators. Their fierce loyalty to anemones grants them a safe haven in reefs full of shifting alliances. Everything about their existence feels improbable, yet everything about it is rooted in evolutionary finesse. As the day wanes, the reef dims under the soft lavender glow of descending twilight. The anemone retracts slightly, its tentacles shortening as nighttime predators stir. The clownfish retreat deep among the folds, settling into rest with slow, pulsing movements. Their bodies press gently against the stinging arms that no longer sting. Within the shelter, the dominant female rests near the male, their positions unmistakably defined. Lower-ranking individuals nestle close, but not too close, maintaining the spacing dictated by hierarchy. Night wraps the reef in quiet. The anemone's shape becomes vague in the darkness, but inside its folds, a society persists. A world where fathers become mothers, where fish wear chemical armor, and where survival is negotiated through a partnership between a poisonous host and an adaptable tenant. Clownfish thrive by breaking rules of sex, of territory, of defense, rewriting expectations with every generation. In a landscape shaped by danger, they have chosen a singular path. Create a home inside the jaws of a killer. Rule it through discipline and transformation, and trust that chemistry and social order together can keep chaos at bay. In the gentle sway of a shallow reef, where sunlight filters through water in shifting lattices of gold, an object resembling a delicate bloom dances with the tide. Its tentacles shimmer with soft translucence, their tips glowing faintly as though touched by firelight. From a distance, the sea anemone looks like nothing more than a flower caught in a slow-motion breeze, a quiet ornament on the ocean floor. Yet as the camera moves closer, the illusion of fragility dissolves. Each tentacle is not a petal, but a weapon. Each soft fold hides lethal machinery. The anemone is not a passive plant anchored to the substrate. It is a predator, waiting with unwavering patience. The tentacles are arranged in a ring around a central opening, each one filled with countless specialized stinging cells called nematocysts. These cells are some of the most sophisticated biological weapons in the animal kingdom. Inside each one lies a microscopic harpoon coiled under immense pressure. When triggered by touch or chemical cues, the harpoon explodes outward in a fraction of a heartbeat, puncturing the prey and injecting venom. The speed of this discharge is among the fastest cellular movements known. For small fish or crustaceans, the effect is immediate. Muscles freeze, gills seize, and escape becomes impossible. The camera lingers on a tentacle as a tiny juvenile fish drifts too close. The fish, barely the length of a fingernail, brushes against the anemone's surface. Instantly, multiple nematocysts fire. The fish spasms once, twice, then falls still, suspended like a bead on a string of invisible threads. The anemone begins its slow, deliberate feeding ritual. Tentacles curl inward, guiding the immobilized prey toward the central mouth. This opening, despite its flower-like appearance, functions as both entrance and exit for food and waste. It stretches to envelop the prey, folding inward until both tentacle and fish disappear into the anemone's inner chamber. Once inside, enzymes begin their work. Soft tissues break down. Nutrients move through the anemone's gastrovascular cavity, distributed by simple but effective currents generated by ciliary movement. The feeding takes time, hours, sometimes longer. But for an organism with no need to chase, patience is the most efficient strategy. Every swallowed fish becomes energy for growth, for repair, for reproduction. The anemone thrives through stillness. Yet the storied life of an anemone extends far beyond predation. Around many anemones, a small ecological community orbits, built through partnerships that blur the boundary between defense and hospitality. The most iconic of these is the alliance with clownfish. As clownfish brush tentacles and coat themselves in chemical mimicry, they gain safe haven from predators. In exchange, they drive away anemone-eating butterfly fish, remove parasites, and increase oxygenation by fanning their fins. The anemone, though motionless, becomes the center of a dynamic living system, but clownfish are only one type of ally. In certain regions, anemones host small porcelain crabs that hide among the tentacles. These crabs filter plankton from the water, while relying on the anemone's venomous arms for protection. They remain unscathed because they rarely touch the stinging areas directly, maneuvering with careful precision developed through instinct. The anemone tolerates them because they pose no threat and occasionally clean debris from the tentacles or remove parasites. This is symbiosis, written in cautious movements and mutual benefit. Shrimp also find refuge here, particularly species like the anemone shrimp, whose transparent bodies shimmer with iridescent spots. These shrimp live among the tentacles with near invisibility, protected by their host while scavenging leftover food particles. They groom the tentacles, picking away dead tissue or settling algae, acting like caretakers in exchange for safety. The anemone's tentacles pulse gently as these shrimp crawl across them, creating a sensory map of the surrounding world that helps detect changes in water flow, prey activity, or chemical signatures. Beneath the tentacles, the anemone's base anchors it to rock or coral rubble. Some species possess a broad foot that grips tightly, resisting the tug of waves. Others bury themselves in sand, leaving only their tentacles exposed. The column between foot and tentacles varies in color and pattern, depending on species and habitat. Some display swirling gradients of purple and green, others resemble mottled stone. This diversity reflects the ecological span of anemones, which inhabit not only reefs, but also tide pools, deep sea vents, and even polar waters. Their ability to survive across environments speaks to resilience woven into their deceptively simple anatomy. Anemones reproduce in ways that mirror the complexity of their lifestyles. Some spawn by releasing eggs and sperm into the water column, entrusting the future to currents that scatter larvae far across the reef. Others reproduce asexually by splitting in half or budding from their base. These cloned offspring settle nearby, often forming clusters that create dense patches of tentacles, miniature forests teeming with hidden interactions. A large anemone can live for decades under ideal conditions. Some scientists speculate that certain species may live for centuries if undisturbed. Despite these strengths, anemones face threats intensified by human influence. Rising ocean temperatures cause bleaching, a phenomenon in which anemones expel the symbiotic algae that provide them nutrients and vibrant color. Bleached anemones lose energy and become vulnerable to starvation. Pollution, particularly sediment runoff and chemical contaminants, interferes with their feeding and reproduction. Overharvesting for aquariums removes key species from fragile ecosystems that depend on their presence. And physical damage to reefs reduces available habitat for their attachment. The camera shifts to a storm-swept coastline where waves crash over a rocky ledge. Here, an anemone clings to a tide pool, its tentacles retracting as the water level drops. In this intertidal world, conditions are harsher, temperature fluctuates. Salinity changes rapidly with rainfall. Sunlight can scorch exposed tissue, yet many anemones endure by contracting into tight, protected spheres, trapping moisture inside. When the tide rises again, they unfurl with careful slowness, tentacles reaching outward with renewed purpose. A passing fish brushes the tentacles and is caught immediately. The tentacles wrap, fold, and draw inward with inexorable determination. Watching this process reveals a predator defined not by speed or aggression, but by precision of design. Every movement is efficient, every structure contributes to survival. Even the lack of a central brain. Anemones rely instead on a diffuse nerve net. Reinforces the idea that coordination can arise from simplicity, that complex behaviors need not require complex architecture. In reef systems, the presence of anemones creates microhabitats where numerous species interact. Clownfish defend territory around their host, chasing away trespassers and inadvertently expanding the anemone's sphere of influence. Crabs scuttle beneath the tentacles, stirring sand and bringing nutrients upward. Shrimp sweep debris and alert the anemone to subtle disturbances. The anemone, stationary but vigilant, provides shelter and defense, its venomous arms forming a perimeter that defines the boundaries of this miniature ecosystem. One striking observation emerges as the camera zooms back. No two anemones behave exactly alike. Some wave their tentacles widely, maximizing contact area to capture prey. Others keep their tentacles partially retracted, conserving energy in low food environments. Some host multiple clownfish, others remain solitary. Environmental conditions, current strength, water clarity, temperature, prey abundance, shape each anemone's strategies subtly but meaningfully. What appears as a simple flower is, in reality, a responsive animal adjusting constantly to the rhythms of its surroundings. Night falls across the reef, and the anemone enters a different mode. Many species retract slightly in darkness, reducing exposure to nocturnal predators, but the tentacles remain ready. A small fish, disoriented by the dimming light, wanders too close. It barely grazes the anemone's edge. Nematocysts fire with ruthless precision. Within seconds, the fish is immobilized. The anemone's tentacles lift it, presenting the meal to the central mouth. The reef around it quiets into the hush of night, broken only by the faint crackle of snapping shrimp in distant crevices. Within the folds of this predator, life continues. Symbionts rest. Clownfish hover nearby in rhythmic pulses. Crabs tuck themselves into protected crevices. The anemone's stillness belies the dynamic ecosystem it maintains. It is not simply an animal. It is a fortress, a weapon, a nursery, a partner, a landscape in miniature. As the chapter closes, dawn creeps over the reef once more. The anemone's tentacles expand fully into the gentle light. They sway like petals greeting the day, disguising the lethal precision beneath their soft edges. The reef stirs awake around them. And in the quiet rhythm of the tide, the anemone stands as a reminder that beauty in nature often conceals danger. And danger often conceals intricate, essential roles in the web of life. In the soft twilight of a falling tide, the rocky shoreline reveals a world where colors mute into shades of slate, rust, and pale green. Pools of seawater cling to depressions in the stone, their surfaces trembling with each distant wave. Inside these shallow pockets, the creatures that remain must navigate a temporary prison of exposed light and cooling air. Among them lies a familiar silhouette, a starfish, its 5 arms spread outward like a relic of some forgotten constellation. To the casual observer, it seems motionless, almost decorative, a harmless ornament washed in by the sea. Yet beneath the quiet stillness lives one of the ocean's most peculiar and underestimated predators. The starfish lifts slightly on its tube feet, hundreds of tiny, fleshy pillars lining the underside of each arm. They extend and contract in synchronized waves, gripping the rock with a whisper-soft suction. The movement is slow, deliberate, and almost meditative. But this gentle creeping belies the starfish's capacity for destruction, subtlety, and regeneration, all carried out through an anatomy unlike that of any other large marine animal. The camera follows the starfish as it moves toward a cluster of mussels wedged into a narrow crevice. For many sea creatures, mussels present an insurmountable challenge. Their shells clamp shut with impressive force, resisting attempts by fish, crabs, and even birds to pry them open. But the starfish possesses a weapon built not from speed or strength, but from persistence. It drapes its body over the mussels, wrapping its arms securely around them. Tube feet find purchase on both sides of the shells. Then the starfish begins to pull. This pulling does not resemble the frantic tugging of other predators. It is a patient, unyielding effort, a constant pressure applied from dozens, even hundreds of tube feet coordinating with perfect precision. The mussel resists. The starfish does not relent. Over minutes or hours, the steady force exhausts the mussel's muscles. The shell gapes, first by a sliver, then by a fraction more. That fraction is all the starfish needs. It begins its strangest act of predation. From the center of its body, the starfish extrudes its stomach outward, turning itself inside out. The bright, fleshy mass slides between the mussel's parted shells, filling the cavity with digestive enzymes. The mussel, still alive, undergoes dissolution from within. Tissues soften, nutrients break down into absorbable forms. The stomach gradually envelops everything edible. Once digestion completes, the stomach retracts back into the starfish's body, carrying the liquefied meal with it. Few predators on Earth consume prey this way. Reaching inside, digesting externally, and drawing nutrients inward only after the process has progressed significantly. For the starfish, this technique avoids the need for specialized teeth or crushing appendages. It allows access to prey that rely on armored defenses. It is a slow-motion attack, but one perfectly suited to the intertidal world. As the starfish finishes its meal, the camera shifts to reveal an astonishing detail. One of the starfish's arms is smaller than the others. It tapers slightly differently, its coloration subtly mismatched. This is no deformity. It is the aftermath of regeneration, a process as remarkable as the strange feeding habit. Starfish can regrow entire limbs when lost to predators, environmental hazards, or injury. In some species, an arm torn away carries enough of the central disc to regrow a full new individual. These animals are capable of self-repair at a level most creatures could never achieve. Regeneration begins with wound closure. Cells migrate to the injury site within hours, forming a seal that prevents infection and fluid loss. Beneath this protective layer, undifferentiated cells begin multiplying rapidly. They organize themselves, guided by chemical signals and structural cues, into tissues that rebuild nerves, muscles, water vascular components, and external plates. Over months, the new limb extends outward, gradually forming tube feet and restoring full function. The capability is not merely restorative, it is protective. Losing an arm becomes a survivable event, even strategic. A starfish may shed a limb if seized by a predator, sacrificing a piece of itself to escape. The camera moves deeper along the reef, where sunlight diffuses into softer hues and corals begin to dominate the landscape. Among these structures lives one of the starfish's most notorious relatives, the crown-of-thorns starfish. Unlike the gentle tide pool species earlier in the chapter, this creature sprawls across the reef like a spiked, living disc, its many arms tipped with venomous spines. Its coloration, mottled purples, greens and reds, blends unsettlingly well with the coral environment, but its feeding habits differ in scale and consequence. Where the common starfish consumes individual mussels or clams, the crown-of-thorns starfish targets coral itself. It lifts its body slightly, presses its stomach against the coral's surface, and digests the living tissue layer by layer. Behind it, the coral skeleton remains bleached white, a ghostly scar marking its path. In normal numbers, these starfish are part of the reef's natural cycle, clearing patches where new corals eventually recruit. But when their populations surge, often due to human-induced changes in nutrient runoff or predator declines, the effect is devastating. The camera glides above a reef ravaged by such an outbreak. White patches spread like frost across the coral, connecting into larger networks of damaged terrain. Crown-of-thorns starfish move slowly through this wasteland, their arms curling and flexing as they consume what remains. Each one can eat large sections of reef in a matter of days. When thousands gather in dense swarms, entire reef systems can collapse. The destruction occurs quietly. No explosive violence, no dramatic chases. Only the steady, relentless consumption of organisms that took decades or centuries to grow. Understanding how an animal so seemingly simple can cause such large-scale effects reveals the importance of ecological balance. Crown-of-thorns outbreaks often correlate with declines in their natural predators. Certain species of giant snail and triggerfish consume them, but pressures such as overfishing or habitat degradation reduce predator numbers. With fewer natural checks, the starfish reproduce freely. Each female can release millions of eggs in a single spawning season, and when larvae encounter nutrient-rich waters, often linked to agricultural runoff, survival rates soar. Not all starfish pose such large-scale risk. Many species live quietly within kelp forests, seagrass beds or rocky coastlines, their presence integral to ecosystem functioning. Some graze algae, others feed on detritus. Still others target specific prey, helping maintain biodiversity. Their roles vary, but they always influence the landscape subtly, persistently, and often unnoticed. In deeper waters, a starfish glides across a sandy slope, its movement ghost-like in the dimness, bioluminescent plankton spark beneath its tube feet. The starfish pauses near a buried clam, sensing chemical cues through receptors along its arms. Without eyes in the traditional sense, starfish navigate the world through a combination of chemical gradients, touch, and diffuse light detection. Each arm contains a nerve cord, functioning semi-independently, yet coordinating with the entire body through the central nerve ring. This decentralized system allows continued function even if parts are lost. A starfish does not think the way vertebrates do, but it does perceive, respond, and adapt with remarkable efficiency. As the tide shifts and currents strengthen, the starfish anchors itself firmly. Tube feet attach with temporary adhesive secretions capable of holding against significant force. When the starfish chooses to move, the adhesive dissolves without residue. This reversible bonding has inspired materials science research, demonstrating once again that seemingly simple organisms can hold complex secrets. Night deepens across the reef, shadows lengthen. Nocturnal hunters stir from crevices, but the starfish feels no urgency. Its vulnerability lies not in motion, but in exposure. With a body built low to the substrate, with armor like ossicles beneath its skin, and with the ability to shed limbs when threatened, it relies on passive defenses combined with slow, deliberate strategy. Unlike faster animals that must constantly flee danger, the starfish endures by being difficult to consume, difficult to kill, and capable of rebuilding itself if injured. The camera returns to the tide pool from earlier in the chapter. The starfish there has finished its meal and now rests motionless, arms extended once more. The water reflects the deepening colors of evening. Waves creep slowly back into the pool, bringing new scents, new grains of sand, new possibilities of prey. The starfish remains ready, waiting not with anticipation, but with the quiet certainty of an animal whose survival does not depend on speed or aggression, but on persistence, adaptability, and a biology that rewrites the boundaries of regeneration. In the end, starfish embody a paradox: gentle in appearance, slow in movement, yet capable of feats of predation and self-repair unmatched by most marine life. They shape ecosystems through patient pressure. They overcome injury through cellular ingenuity. They can become, under certain conditions, either essential architects of biodiversity or architects of destruction. They are reminders that in the ocean, power does not always come with teeth or speed. Sometimes it comes with the ability to begin again. One arm, one cell, one relentless movement at a time. Dawn creeps slowly across a shallow lagoon, casting soft ribbons of gold across the water's surface. Beneath the shimmer, long blades of seagrass sway as though breathing, creating a rippling meadow that stretches toward the reefs. Tiny bubbles cling to the leaves, rising in lazy spirals whenever the current stirs them loose. Small fish dart between the green blades, pausing to nibble algae or hide from passing shadows. To the untrained eye, this meadow seems peaceful, almost untouched. But the subtle trails carved through the grass reveal the presence of one of the ocean's oldest landscape architects, the green sea turtle. A rounded silhouette glides into view, cutting through the water with the heavy, deliberate grace of something that has crossed oceans for millions of years. Its shell is thick and ornate, shaped by eons of evolutionary pressure and textured with patterns that catch the shifting light. The turtle's flippers move in slow, steady strokes, more like wings than limbs, each movement generating a broad push of water that propels the creature forward with surprising efficiency. Despite its bulk, it travels with a calm certainty. Unhurried, yet unstoppable, the turtle lowers its head and begins to graze. Its beak, sharp-edged, serrated, and curved like a gardener's shears, slices through the seagrass with practiced ease. With each bite, it removes only the upper portions of the blades, leaving the roots intact. This technique is essential. By cropping the grass rather than uprooting it, the turtle stimulates regrowth. The trimmed blades grow back brighter, younger, and more oxygen-rich. A meadow visited regularly by turtles looks vastly different from one left untouched. Without grazing, seagrass becomes long, coarse, and covered in epiphytic algae. Oxygen levels drop, sediment clouds, and the meadow begins its slow decline. With turtles, the grass stays short, healthy, vibrant. A living lawn maintained by ancient herbivores. As the turtle grazes, clouds of tiny organisms scatter. Small shrimp leap from blade to blade. Fish forage in the turtle's wake, snapping up particles dislodged by its powerful bites. Grazing is not merely feeding, it is disturbance, renewal, and redistribution. The turtle's role in this meadow extends far beyond its own survival. By cropping the seagrass, it encourages nutrient cycling and increases the photosynthetic capacity of the ecosystem. In many tropical lagoons, the health of seagrass beds correlates directly with the presence of green turtles. The turtle lifts its head, strands of grass drifting away as it exhales a slow stream of bubbles. Its eyes, dark and glossy, reflect not curiosity, but the steady awareness of an animal shaped by time rather than novelty. Green turtles are among the oldest lineages of marine vertebrates. They have survived epochs of shifting continents, warming oceans, and mass extinctions. They move through modern waters like living relics, their bodies carrying the memory of ancient seas. The camera follows as the turtle glides past the meadow and heads toward deeper water. Its movements become more fluid as depth increases. The surrounding landscape shifts from seagrass to coral rubble, then to vast expanses of open blue. In these deeper waters, green turtles transition from gardeners to travelers. Their migrations span entire ocean basins. From feeding grounds in shallow lagoons, They journey across hundreds or even thousands of kilometers to reach nesting beaches on remote coastlines. These migrations are navigational feats that surpass those of many birds and mammals. Science continues to investigate how turtles navigate such distances with such reliability. One key lies in the magnetic field of the Earth. Hatchlings, upon leaving their natal beach, imprint on its unique magnetic signature, a combination of field strength and inclination specific to that coastline. Years or decades later, mature turtles use this magnetic map to return to the very same beach where they were born. The precision of this navigation is astonishing. Even after crossing wide stretches of open ocean with no visual landmarks, they locate their birthplace with remarkable accuracy. Their internal compass, forged from magnetoreception, guides them across currents, storms, and the monotony of blue water. As the turtle moves farther from shore, the water deepens to a cool, muted turquoise. Sunlight still penetrates, but in softer beams. The turtle rises occasionally to breathe, breaking the surface with a quiet exhale before slipping beneath again. Its shell, though armored, carries scars. Rough patches where barnacles once grew, lines where old injuries healed, chips from close calls with predators or boats. These markings record a life lived in the open ocean, a biography etched in keratin and bone. Along its migration path, the turtle encounters a drifting patch of algae. Sargassum formed into a floating mat. Juvenile fish dart between the fronds. Crabs cling to the tangled structure. The turtle inspects it briefly, though adults feed primarily on seagrass and algae. Its digestive system is adapted for terrestrial-like vegetation, unique among marine reptiles. Inside its gut, fermentation and enzymatic processes break down cellulose that many marine animals cannot digest. The turtle's diet, though seemingly simple, fuels long migrations and contributes to the cycling of nutrients across ecosystems. The camera transitions back to the coastal meadow as another turtle, younger, smaller, grazes with less precision. Its bites remove larger sections of grass, sometimes pulling at roots. This difference reflects the learning curve experienced by young turtles. Grazing technique improves with age. Younger individuals often create patchy areas, which still benefit the meadow by reducing overgrowth, but lack the efficiency of mature grazers. Over time, the turtle will refine its technique until it becomes a master sculptor of seagrass beds. In regions where turtles are abundant, entire coastlines evolve under their influence. Seagrass beds remain trimmed, oxygenated, and structurally diverse. Fish populations flourish within these maintained habitats. Water clarity improves as the grass traps sediment without smothering itself. Where turtles decline, the opposite occurs. Seagrass becomes overgrown, smothered by algae, or uprooted by storms due to weakened root systems. Ecosystem collapse can be slow, subtle, and devastating. The turtle's importance extends beyond seagrass. Their nesting sites transform beaches by redistributing nutrients from the ocean to land. Eggs that do not hatch contribute nitrogen and phosphorus to coastal plants. Hatchlings that fall prey to predators feed terrestrial birds and crabs. Even the act of digging nests aerates the sand, improving conditions for other burrowing organisms. The green turtle's influence reaches across ecosystems, linking land and sea in a nutrient cycle older than human civilization. But the turtle's life is not without threat. Fishing nets, boat strikes, pollution, habitat loss, and climate change all chip away at populations. Seagrass meadows, essential to the turtle's diet, have declined significantly worldwide due to coastal development and declining water quality. Nesting beaches face erosion, artificial lighting, and rising temperatures. Temperature influences sex determination in turtle hatchlings. Warmer sands produce more females. Climate change threatens to skew this balance drastically, creating generational instability in populations, yet green turtles persist. Their resilience, honed over tens of millions of years, remains strong. Conservation efforts that protect nesting beaches, reduce bycatch, restore seagrass, and minimize pollution have led to local population recoveries in several regions. When given space and time, turtles rebound, meadows regenerate, coastal ecosystems regain their rhythm. The camera returns to the turtle grazing in the meadow. Small fish gather around it, feeding on scraps and cleaning algae from its shell. The turtle grazes steadily, indifferent but purposeful. Each bite reshapes the meadow. Each slow movement contributes to the balance of light, oxygen, and sediment. It is neither predator nor prey in this moment. It is an ecosystem engineer, a force that transforms landscapes through patience rather than aggression. As the tide rises, the meadow brightens. Waves ripple through the grass, bending the blades in sweeping arcs. The turtle lifts its head, glides forward, and disappears into the shimmering distance. The meadow continues to sway behind it, renewed by the creature that has shaped it since ancient seas covered primordial shores. The green sea turtle stands as a paradox, armored yet gentle, ancient yet essential to modern ecosystems, a slow-moving grazer that influences coastlines on a scale rivaling storms. It is not merely a survivor of deep time. It is a gardener of oceans, an architect of meadows, and a traveler guided by magnetic whispers across the blue. In a world defined by change, the turtle endures, patient, persistent, and indispensable. In the dim blue half-light of the continental shelf, where sunbeams weaken and shadows lengthen into soft gradients of green and grey, a world of stone, sand, and slow movement unfolds. The sea floor here is a labyrinth of crevices, overhangs, and scattered boulders shaped by storms and ancient geological shifts. Algae cling to rock faces like coarse velvet. Plumes of silt drift upward when a wave pulse passes overhead. The landscape feels almost prehistoric, a fitting stage for one of the ocean's most enduring survivors. From beneath a rocky ledge, two long antennae extend cautiously. They sweep the water like sensitive instruments, tasting chemical traces, detecting faint vibrations, reading the terrain without sight. Only after several moments does the creature reveal itself. A lobster, armored in segmented plates, moving with a mix of precision and ancient purpose. Its carapace glints faintly in the filtered light, etched with scars and tiny imperfections marking years of survival. It crawls forward, claws held outward like twin shields. Tools evolved not just for feeding, but for negotiation, combat, and defense. The lobster's body is a masterpiece of natural engineering. Its exoskeleton, composed of chitin reinforced with calcium carbonate, forms articulated armor that bends at flexible joints without compromising protection. Each segment interlocks with the next, allowing the creature to navigate narrow crevices or arch backward in sudden retreat. Beneath the shell lies a muscular core designed to power the animal through water when necessary, though lobsters prefer the firm traction of the substrate. Their walk, sideways, deliberate, oddly graceful, gives the impression of a creature inspecting every detail of its world before committing to a path. The claws immediately demand attention. One, typically larger, thickens into a crushing claw capable of applying extreme force. The other, slimmer and lined with serrated edges, functions as a slicing claw. Together, they form a paired system of offense and manipulation. When the lobster tests its claws against shells or detritus, the power becomes clear. The crushing claw can break open mollusk shells and crack crab carapaces with ease. Experiments have measured crushing forces strong enough to pulverize bone or sever fingers. This is not aggression, but adaptation. In a world where prey hide beneath armor, success belongs to those who can break through it. The lobster stops at the entrance of a narrow crevice, antennae twitching. Scent molecules drift through the water, the chemical signatures of small fish, worms, and other crustaceans tucked between stones. Lobsters rely more on smell and touch than sight. Their eyes are compound structures that detect motion and contrast, but offer limited detail. Through antennae and sensory hairs along their legs, they build a mental map of their surroundings. They detect the faintest scent trails of wounded animals. They recognize the chemical traces of rivals or mates. In darkness, these sensory systems become their primary guide. The lobster pushes deeper into the crevice, searching for food. When it finds a clam, it positions the crushing claw and brings it down with measured force, cracking the shell. The slicing claw then extracts soft tissue in delicate movements. Despite their powerful appearance, lobsters often feed with surprising finesse, peeling and extracting rather than shredding outright. The feeding behavior reflects a creature that must balance efficiency with energy conservation. Every action underwater demands fuel, and in ecosystems where prey availability fluctuates, energy must be spent wisely. When danger approaches, the lobster retreats with astonishing speed. Using a rapid flex of its abdomen, it snaps backward in a cloud of silt, propelled like a spring-loaded arrow. This jet-like escape is fueled by powerful abdominal muscles hidden beneath the armor. Predators such as cod or octopus may lunge, but the lobster's sudden retreat often outpaces the attack. The speed contrasts sharply with the lobster's normal slow gait, reminding us that beneath the heavy armor lies a body capable of remarkable agility. Yet one of the most extraordinary aspects of lobster biology lies within the armor itself, the shell that both protects and restricts. Because the exoskeleton cannot expand, lobsters must shed it periodically in a process called molting. Molting is risky, energy-intensive, and essential for growth. Before the molt, the lobster absorbs some of the calcium from its shell, softening the structure. It draws in water to swell its body, cracking open the old exoskeleton along weak points. Slowly, laboriously, it pulls itself free, soft, vulnerable, and unarmored. Immediately after emerging, the lobster's new shell is pliable, offering no defense against predators. For hours or days, the lobster hides, sometimes burying itself beneath sand or wedging deeply into a crevice. During this time, the body expands, taking in water to stretch the new form to a larger size. As the shell hardens, minerals deposit into its structure, preparing the animal for its next phase of life. Molting occurs many times in the early years, and less frequently as the lobster grows large. Each molt brings the potential for regeneration. Lost claws grow back, damaged antennae are replaced. Even eyes in some cases regenerate. Molting grants lobsters biological renewal. The consequences of this continuous shedding extend far beyond simple growth. Unlike most animals, lobsters show no clear signs of age-related decline. Their cells maintain robust DNA repair mechanisms, and their telomerase activity, an enzyme linked to cellular longevity, remains high throughout life. Scientists debate how long lobsters can live under ideal conditions. Some estimates suggest many decades. Others believe they can surpass a century. Large lobsters, often weighing several kilograms, may be several tens of years old. They do not age in the conventional sense. Instead, they grow, molt, and continue on, limited only by predation, disease, or catastrophic events. The camera reveals a larger lobster emerging from its shelter at dusk. Its massive claws and thickened shell indicate maturity. With age comes territory. Large lobsters fiercely defend burrows, displacing smaller rivals. Their dominance shapes local ecosystems, determining access to shelter and resources. Competing males sometimes engage in ritualistic combat, antennae whipping, claws raised, bodies arching. Unlike the quick aggression of fish, lobster disputes unfold slowly, with displays that communicate strength and intent. When fights do escalate, the crushing claw becomes both weapon and warning. Yet most conflicts end with one lobster retreating, the cost of injury too high to risk. Night descends across the reef, and the lobster becomes more active. Lobsters are largely nocturnal, emerging from shelters to forage across sandy bottoms or rocky ledges. They navigate with confidence, antennae sweeping like searchlights through the dark. In some regions, lobsters migrate seasonally, walking in long lines across the sea floor, one behind the other, forming living chains that stretch for dozens of individuals. These migrations reflect environmental cues, such as water temperature or storm patterns, suggesting coordination far more complex than previously understood. The lobster halts suddenly as a shadow passes overhead. An octopus drifts down from a rock, its tentacles trailing like wisps of smoke. The lobster raises its claws instinctively, presenting them outward in a defensive posture. The octopus reaches forward, testing with a tentative arm. The lobster snaps its claw shut, sending a sharp vibration through the water. The message is clear. Octopus predation is a serious threat. Their agility and intelligence allow them to pry open or disable armored prey. But a large lobster can inflict damage with the crushing claw, making the encounter dangerous for both. The octopus retreats, melting back into a crack in the rock. The lobster lowers its claws but remains still for several moments, the near miss lingering in the dark water. As dawn returns, the lobster settles back beneath its ledge, antennae extended as always. Its world consists of cycles: feeding, defending, molting, migrating, each shaping the landscape in subtle ways. Lobsters influence populations of mollusks and smaller crustaceans. They create shelter opportunities when they excavate burrows. Their molts deposit mineral-rich shells that become substrate for algae and small invertebrates. Even their deaths contribute nutrients to the seafloor. They are more than armored hunters. They are participants in a complex, interdependent system, yet their resilience does not make them invulnerable. Humans harvest lobsters extensively, often targeting large breeding individuals whose removal can destabilize local populations. Climate change alters water temperatures, influencing growth rates and migration patterns. Diseases, once rare, spread more easily in warming waters. Habitat degradation reduces shelter availability. The lobster, ancient and adaptable, now faces challenges unprecedented in its long evolutionary history. Still, the lobster endures. Its body, armored yet flexible, ancient yet continually renewed, reflects an organism designed for persistence. Its claws deliver crushing power, but its antennae deliver sensitivity. Its shell restricts growth, yet its molt grants rebirth. It is a creature of dualities, strong but slow, armored but vulnerable during transformation, solitary but sometimes migratory, capable of enormous longevity, yet dependent on the fragile balance of marine ecosystems. The camera pulls back as the lobster settles deeper into shadow, the soft glow of morning filtering through cracks in the rock. Its antennae curl gently, its claws rest on the substrate. It waits, patient, enduring, unchanged by the currents rushing past. In a world defined by movement, the lobster remains a constant, a quiet force shaped by time, armor, and the ancient rhythm of renewal. It is not merely a tank of the seafloor. It is a survivor of eras, a creature that grows not by outrunning the world, but by outlasting it. The story of the crab begins long before one appears on the screen. It begins in the slow grinding of tides, the rise and fall of continents, and the relentless pressures that shape bodies over millions of years. Across the world's shorelines, in mangroves, reefs, sandflats, estuaries, kelp forests, deep-sea vents, and even high mountain streams, the same unmistakable silhouette keeps reappearing. A flattened, armored body, legs splayed wide, a pair of claws held forward like living grappling hooks. This shape has emerged again and again in unrelated lineages, as if evolution keeps forgetting it already invented the crab and then inventing it again. Biologists have a word for this strange pattern: carcinization. The tendency of many crustaceans to evolve toward a crab-like form. It is as if nature keeps returning to the same solution, refining it like a favored blueprint for survival. The crab is not a single creature, but an idea that keeps proving itself. In the shallows of a rocky coastline, where waves surge and retreat in endless breathing cycles, a crab clings to the underside of a boulder. Its legs grip the stone with small hooked tips that anchor it, even as the water pulls with the force of a storm. Barnacles, algae, and seaweed fragments drift past like wandering confetti. The crab remains motionless at first, letting the turbulence pass. Its body resembles a shield, a wide, flattened carapace that deflects pressure from above and hides the soft organs beneath. When the wave subsides and the water thins to a shimmering film, the crab moves quickly. Sideways steps allow instant acceleration. The joints of each leg coordinate with exquisite precision, turning what might appear comically angular into one of the most stable modes of motion on uneven terrain. As it scuttles across the rock surface, grains of sand scatter in brief arcs behind it, and the creature's claws click softly in the air. The origin of this sideways gait lies not in awkwardness, but in mechanical advantage. Crab legs hinge sideways, giving them greater leverage against the ground. This posture spreads their weight evenly, stabilizes them on shifting sediment, and allows rapid response in any direction. In ecosystems where predators arrive from above, below, and behind, the ability to pivot instantly becomes a survival tool more reliable than speed itself. When viewed from above, the crab resembles a living landmine, compact, armored, capable of explosive bursts of movement in multiple directions. A gull glides overhead, its shadow sweeping across the rocks. The crab freezes. Remaining still transforms it into part of the landscape. Many species have shells colored to match sand, mud, coral, or stone. Evolution has fine-tuned their camouflage until even trained observers struggle to distinguish the animal from debris. Only when the gull veers away does the crab resume its journey, crossing a narrow tide pool with cautious, deliberate steps. Underwater, its movements shift from quick scuttling to a weightless glide, legs paddling lightly. A thin film of oxygen clings to the hairs on its body, allowing it to breathe underwater by continuously wetting its gills. Some crabs even retain small reservoirs of seawater beneath their shells, letting them forage on land for extended periods as long as their gills remain moist. The crab pauses near a fissure in the rock. Inside lies a cluster of mussels anchored tightly by byssal threads. The crab's claws, one often larger than the other in many species, begin probing among the shells. The larger claw is a crushing tool, a biological hammer designed to crack open mollusk armor. The smaller claw is nimble, capable of turning and manipulating food with surprising delicacy. The crab works patiently, applying force measured not by brute speed, but by exact angle and pressure. When the crushing claw finds a gap, it snaps shut with immense strength. The mussel's shell cracks. The crab shifts to the finer claw, extracting the soft tissue with surgical precision. This dual-tool design echoes a deeper truth. Crabs are not mindless scavengers, driven only by instinct. They are engineers of their environment. Many species excavate elaborate burrows with chambers for shelter, molting, and storing food. Others collect objects from their surroundings: shells, algae, sponges, even discarded human debris, and attach them to their backs for camouflage. Some, like decorator crabs, create living disguises by allowing sponges or anemones to grow on their shells. This behavior is not random. Crabs choose specific materials for their protective value, demonstrating selectivity and planning. Further along the reef, a different scene unfolds. The tide has receded, leaving a stretch of exposed sand where a dead fish lies stranded. Within minutes, crabs begin appearing from cracks, burrows, and rock overhangs. One arrives, then another, then dozens more. They swarm the carcass with coordinated efficiency. Claws tear at flesh, legs jostle for position. Small individuals grab scraps and dart away before larger crabs push them aside. The sound of chitins scraping against bone is faint beneath the rhythmic rush of the returning tide. Scavenging events like this reveal the sheer biomass of crabs hiding within coastal ecosystems. They are the ocean's cleanup crew, converting death into nutrient-rich fragments that feed worms, bacteria, and microfauna. The speed at which they reduce a carcass underscores their ecological importance. Yet the crab's resilience is tied not only to its armor and claws, but also to its remarkable ability to regenerate. Losing a limb is not the end. During molting cycles, crabs regrow legs, claws, and antennae. Even significant injuries repair over time, as long as the crab survives until its next molt. This regenerative capacity shapes their behavior in fights. A dominant crab may rip the claw from a weaker rival, knowing it reduces competition without killing the opponent outright. The injured crab retreats, survives, and eventually regrows its limb, though often at a smaller scale. Over several molts, the limb can return to full size. This flexibility grants crabs a second chance in a world where injury is common. The molting process itself is a dramatic transformation. The crab must split its hard shell along predetermined seams and crawl out of it like a creature shedding an iron suit. The new exoskeleton beneath is soft and translucent. For hours or days, the crab hides, unable to defend itself. During this vulnerable period, the animal absorbs water to expand its size, stretching the new shell before it hardens. Once rigidity returns, the crab is larger, stronger, and often equipped with restored limbs. Growth in crabs is therefore episodic rather than continuous, a series of transformations punctuating their lives. Each molt represents renewal and risk. As the scene shifts from rocky shores to mangrove forests, a chorus of rustling legs and snapping claws fills the air. Fiddler crabs gather along the mudflats, their oversized claws raised like flags. The asymmetrical claws are not used for feeding as one might expect, but for communication. Males wave them in rhythmic displays to attract mates or establish territory. The waving patterns are species-specific, akin to visual language etched in movement. The mud beneath them churns with every step, aerating sediment and redistributing nutrients. In this way, crabs become ecosystem engineers, shaping soil quality and influencing plant growth. On coral reefs, the role of crabs becomes even more complex. Coral guard crabs defend their host corals from predators such as crown-of-thorns starfish. They patrol the coral branches like sentinels, pinching and deterring intruders. In return, the coral provides shelter and food in the form of mucus and trapped plankton. This mutualistic relationship reflects the crab's versatility. Predator in some contexts, protector in others. Far below the surface, in environments where sunlight never penetrates, deep-sea crabs thrive near hydrothermal vents. Here the water is dark and warm, rich with minerals spewed from the Earth's crust. These crabs have adapted to extreme pressure and cold. Their claws harvest bacterial mats growing around the vents, and their bodies host symbiotic microorganisms that help process chemical energy. Even in these alien landscapes, the crab body plan persists, armored, compact, efficient. Still deeper in evolutionary commentary lies the crux. Why do so many organisms evolve into crab-like shapes? Carcinization is one of evolution's strangest recurring themes. Lobsters, shrimps, and other crustaceans have repeatedly converged on the crab blueprint. The flattened body provides stability against waves and currents. The wide stance distributes weight for digging and climbing. The protective carapace shields vital organs. Claws serve as both tools and weapons. This combination of traits offers such a broad advantage that evolution keeps circling back to it, sculpting different species into similar shapes, even though their ancestors diverged long ago. It is as if evolution experiments widely, but always returns to this configuration. Nature's favorite mutant chassis. The perspective widens to show a shoreline at low tide. Crabs of multiple species forage simultaneously. Some scrape algae from stones. Others sift sand for buried worms or detritus. Juveniles dart in erratic bursts across the substrate. A few hide beneath discarded shells. The diversity is immense, yet the underlying architecture is shared. This unity of form combined with diversity of behavior illustrates the evolutionary success of the crab body plan. As currents shift and water rises once more, the crabs retreat to safe zones. The large scavengers vanish beneath rocks. The smaller species disappear into burrows. In a matter of minutes, the sand flat empties. Only faint tracks remain, soon erased by the returning tide. In the end, the crab is more than an armored creature moving sideways across shorelines. It is a pattern written into evolution, repeated across time and geography. It is resilience shaped into biology. It is versatility crystallized in shell and claw. The crab thrives in nearly every marine environment, because its design is not specialized for one niche, but optimized for many. It can scavenge, hunt, dig, defend, regenerate, and engineer its surroundings. It persists through storms, predators, injury, and shifting landscapes. It is, in every sense, the ocean's enduring experiment. A body plan so effective that evolution cannot stop reinventing it. The stingray begins as a shadow gliding across a sunlit seabed, a slow-moving silhouette shaped like a drifting leaf torn free from some underwater tree. Only when the viewer watches closely does the true structure emerge. A wide, flattened body tapering into long, rippling fins that move not with the rigid strokes of a fish, but with waves that spread from the head to the wingtips, as if the ocean itself is breathing through the animal. The spine trails behind like a thin, flexible antenna, sometimes tipped with a spine sheathed in venom. Every movement is precise, efficient, and evolutionary in its intent. The stingray does not swim so much as it levitates through water, holding position just above the sand where the competition is thick and the opportunities are richer than they appear. As the creature glides, sunlight filters through the surface in shifting ribbons, illuminating a mosaic of pale sand, broken shells, and scattered patches of seagrass. The stingray's dorsal surface mirrors this environment so closely that from above it seems to dissolve into the substrate. The coloration is not merely camouflage, but a strategic cloak that hides the stingray from two groups of eyes: the predators patrolling above and the small fish and crustaceans living below. The world of the stingray is a world of layers: currents above, sediment below, and the narrow interface between them, where ambush becomes a lifestyle. This is where the stingray thrives. The body plan, flattened as though pressed between the pages of evolution's notebook, is not the byproduct of some accidental mutation. It is the deliberate architecture of a predator that has abandoned speed in open water for stealth in the shallows. The pectoral fins, widened until they form a continuous disc with the head, act like flexible wings. By generating undulating waves along their edges, the stingray can hover with exquisite control, barely disturbing the water around it. This silent flight allows the animal to approach prey without revealing its presence. Even the shadow it casts is muted, softened by the low altitude at which it travels. To the animals in the sand below, the stingray is simply another shifting pattern of light. When the stingray decides to settle, it does so in a single fluid motion. The body lowers toward the substrate, wings bending subtly, and the animal presses its entire surface into the sand. With a few rapid ripples of the fins, sand particles swirl upward, forming a short-lived cloud that engulfs the ray. Within moments, the stingray is gone, buried beneath a thin veil of sediment. Only two details remain visible: the spiracles, small openings just behind the eyes, pulsing rhythmically as they draw water in from above. This adaptation allows the stingray to breathe without clogging its gills, a crucial advantage when lying in wait for long stretches of time. Buried like this, a stingray becomes a biological landmine. It tracks the world above, not with sight, but with a sensory system woven into its very skin. Along the snout and underside, clusters of gel-filled pores called ampullae of Lorenzini detect the faint electric fields produced by muscle contractions in nearby animals. Even the smallest crustacean generates electrical noise, and the stingray can read this information through sand as though the prey is broadcasting its position. This ability is so refined that the ray can differentiate between the electrical field of a digging crab and the background hum of shifting sediment. In the darkness beneath the sand, vision is irrelevant. Electricity becomes the language of the hunt. A small goby approaches the buried stingray without realizing the danger below. It flicks its tail, sending pulses of electric signal into the water. The stingray's receptors flare with information, distance, direction, and even the rhythm of movement. In an instant, the stingray erupts from the sand. The wings contract inward, and the body folds slightly, forming a funnel that directs water toward the mouth. A powerful suction pulls the goby into the waiting jaws. The entire strike lasts less than a second. The sand settles, the stingray glides forward, and the seabed returns to silence as though nothing transpired. While the graceful hunting tactics of stingrays dominate attention, the defensive architecture is equally extraordinary. Along the tail lies the venomous spine, or in some species, multiple spines, embedded in tissue but ready to break away during a defensive strike. Unlike snakes or scorpions, stingrays do not inject venom proactively. The spine is a passive weapon, triggered by pressure or contact, often used when a predator approaches from behind or when the stingray is unintentionally stepped on in shallow water. The spine's surface is covered in backward-facing barbs that allow it to lodge deeply into flesh. Within its grooves lies a venom that can cause tissue necrosis, severe pain, and in rare cases fatal physiological reactions. Yet despite this fearsome defense, stingrays are not aggressive animals. Their instinct is to flee, relying on speed and stealth to avoid conflict. Most injuries occur when humans enter shallow water and step directly on a buried ray, triggering a reflexive tail strike. The spine detaches, becoming an unfortunate reminder of the stingray's highly evolved toolkit. From a biological perspective, the spine is a masterpiece of deterrence. A final warning that the stingray is not merely a drifting wing, but a well-protected ambush predator capable of inflicting consequences. As the stingray glides away from its ambush site, it passes over the labyrinthine roots of a mangrove forest. Juvenile rays often shelter here, among the twisted branches that rise from the mud like submerged scaffolding. In these protected nurseries, the water is shallow and warm, rich with small fish and crustaceans. Young stingrays learn to navigate complex environments, practicing their burying techniques and refining their electric sensory skills. Their wings beat in shorter, quicker motions, reflecting the need for agility among tight spaces. Growth in stingrays is gradual, tied to the quality of food and the stability of habitat. Moving beyond the mangroves, the scene shifts to a deeper sandy plain where larger stingrays patrol. Here, adults may reach spans of several feet across, though their movements remain surprisingly delicate. A female approaches a male during mating season, her wings sweeping gracefully. Stingray courtship involves synchronized swimming, gentle contact, and coordinated spiraling movements. Though their bodies appear otherworldly, their reproductive strategies are deeply grounded in the challenges of producing offspring in an environment full of predators. Many stingray species give live birth rather than laying eggs. Pups emerge fully formed miniature versions of the adults, capable of swimming and burying themselves within hours. The ecological role of stingrays extends far beyond their predatory habits. By disturbing sediment as they forage, stingrays aerate the seabed, redistributing nutrients and maintaining the health of benthic ecosystems. Their feeding pits create microhabitats that host worms, shrimp, and small fish. This role is often overlooked, yet it is crucial in maintaining the balance of shallow marine environments. Without stingrays, sandflats and seagrass meadows can become compacted, reducing biodiversity and altering the flow of nutrients across coastal zones. A shark enters the frame, its shadow long and unmistakable. Stingrays and sharks share ancient evolutionary histories, both belonging to the group of cartilaginous fishes. The stingray's responsiveness increases as it senses the subtle change in pressure and electricity from the approaching predator. Rather than fleeing outright, the stingray lowers its profile, wings pressed close to the sand. If detected, it will bolt in a sudden burst of speed, wings generating powerful thrust along their entire length. If not, the shark will pass overhead, unaware of the biological aircraft camouflaged beneath it. The scene shifts once more, this time showing the wide-open water of an offshore sandbar. Here, eagle rays arc through the water column in sweeping loops, their wing beats more dramatic and rhythmic than the subtle flutter of bottom-dwelling stingrays. Though close relatives, these rays represent another evolutionary iteration of the winged fish design. Their shape is aerodynamic, their motion reminiscent of birds gliding across invisible currents. Their presence highlights the explosion of diversity within the stingray family, each lineage fine-tuned to its particular ecological niche. As the day fades and shadows lengthen across the seafloor, a single stingray settles once more into the sand. The spiracles pulse lightly, the wings shuffle. A faint dusting of sediment drifts over the body. With the coming darkness, more prey will become active, and the stingray will resume its silent patrol. In its design, one sees not fragility, but the culmination of millions of years of refinement. A creature that trades speed for stealth, visibility for invisibility, energy costly chases for efficient ambush. To many observers, the stingray appears serene, gentle, even harmless. But the truth is far more intricate. Its body is an essay in evolutionary compromise, where every curve, ripple, and sensory system is tuned toward a life lived at the boundary between motion and stillness. It glides not to show elegance, but to erase its own presence. It buries itself not out of fear, but to become a weapon disguised as sand. It listens to electricity, not because it sees poorly, but because it senses the world in a dimension unavailable to most creatures. In the quiet closing moments, the stingray is almost invisible again, hidden beneath its thin blanket of sand. Only the subtle rise and fall of spiracle openings betray life. Beneath that sand lies an organism shaped by ambush, electrical perception, venomous defense, and aerodynamic motion. A gentle-looking kite, engineered by centuries of selective pressure to dominate the seabed, with patience rather than force. The stingray is not merely a creature of the shallows, it is the embodiment of everything evolution can accomplish when a predator chooses silence over speed and invisibility over armor. It is a living wing that swims through shifting landscapes of sand and light, a reminder that the ocean's deadliest designs are often its most graceful.